So, good morning, everybody, and welcome to Computer Vision for Material Science workshop. It's the first workshop in the series, hopefully in the series of similar workshops. And I hope you'll enjoy it. Very briefly about organization of the workshop. So the program is on the web and shown on the screen. We'll have a series of invited speakers. One of them will be doing presentation remotely, couldn't make it at the last moment. And time for questions will be limited, but please keep in mind that all the oral presenters, they will have posters as well, and there'll be enough time to talk to them during poster session. And in the end, as a final event of the workshop, there'll be panel discussion, and all the invited speakers will be present during that panel discussion, so you'll have plenty of time to ask questions you may have. So without further ado, I would like to introduce our first invited speaker, Elizabeth Holm. And Professor Holm has over 25 years of expertise as computational material scientist. Her research areas include the theory and modeling of microstructural evolution in complex polycrystals, the physical and mechanical response of microstructures, mechanical properties of carbon nanotubes networks, atomic scale properties of internal interfaces, machine vision for automated microstructural classification, and machine learning to predict rare events. Computational techniques applied to these problems range from atomic scale through the mesoscale to the continuum scale. A particular focus is identifying useful concepts from data science, including machine learning, machine vision, and network analysis. Prior to joining the University of Michigan, Elizabeth held position at Sandia National Laboratories and Carnegie Mellon University. She has received several honors and awards, is a fellow of ASM International, 2013 president of the Minerals, Metals and Materials Society and organizer of several international conferences, and has been a member of the National Materials Advisory Board. Elizabeth has been inducted as 2019 Fellow of the Minerals, Metals and Materials Society for pioneering achievements and leadership in computational materials science and integrated computational materials engineering. So I'm turning over the screen and mic to Elizabeth.
Thank you very much, Alexei. Let me get these slides up. I was very excited to be invited to this workshop because I think AI has been really a major influence in material science lately, but we tend to lump everything AI into one pot. My specific area of interest in this field is in computer vision. And so I was very excited to see a material science focus here as CVPR. And I very much appreciate your flexibility in letting me participate remotely, even though I wasn't finally able to make it across the country to Seattle. I'm delighted to be here virtually with you today. I want to talk today about the computer vision for microstructural science. I have been a microstructural material scientist for decades now, since the beginning of my career. And I became very excited about the possibilities for computer vision methods, starting before the AI and machine learned methods and moving on to the more modern techniques that we'll talk about today. But one of the persistent challenges with applying these methods to material science data sets is that we tend to have rather modest sized image data sets compared to social media or even medical imaging. And we'll talk a little bit about that as we go. So this talk, I want to emphasize a research area in my group that is stressing quality over quantity, creating methods for computer vision for microstructural images that are frugal in their data needs. And we'll talk about what that means as we go. And I want to acknowledge two of my former students, now graduated and off with their own jobs, Bo Lay and Ryan Cohn, whose work was really helpful in putting this together. So I don't think I have to say anything to this audience about why AI is important to microstructural science, to image data in material science. there are so many possible avenues for benefit to our field, but I like to highlight three in particular that are relevant to the microstructural scientists. The first is that AI, deep learning, can help support us humans in tedious tasks. These are tasks that we can do, but they're boring and they're difficult and they suffer from our lack of ability to pay attention indefinitely. These are tasks like classification of defects, say in images, annotation of images to determine components to segment the image, searching and sorting images, and so on. These are tasks that are done every day in a lot of quality control pipelines, and yet they drive people a little crazy, as you can ask my graduate students who have to annotate images for segmentation. The second area that AI really helps is in difficult tasks, tasks that for one reason or another challenge the human. And these can be identification, where humans may have to have their own extensive training in order to be accurate at an identification task or a categorization task. These are analysis tasks, things where measurements can be difficult to make. Areas where humans can do it, but only after training and only after a lot of hard work. And finally, high dimensional tasks. These are the places where humans may not even be able to immediately contribute. These are where we look for trends, correlations, or make judgments on deep data, on data that has a high dimensional character to it. And it may be very difficult for us humans to even find the high dimensional correlations that we need in order to make the judgments or find the trends that we're interested in. In microstructural science, I show just a couple of examples at the bottom of the slide. One is an annotation challenge where my student was asked to find all of the satellite particles. That's the teeny tiny stuck-on particles that have agglomerated on the larger powder particles that are, happens to be an additive manufacturing raw material powder. What a tedious and difficult task this was. Tedious because there's lots of satellites and you have to go through with a stylus and outline all of them. And difficult because deciding what is and isn't a satellite particle is a judgment call and not an easy one. On the right-hand side of the slide, I show an example of a high dimensional task that humans can't really do, and that is the task of taking an optical micrograph shown on the left and turning it into an SEM micrograph shown on the right. In other words, trying to use optical microscopy in place of scanning electron microscopy because it's cheaper and faster, but still get out the data equivalent of an SEM micrograph. That's a high dimensional task that a human can't learn, but that we have found that a deep learning system can. With that said, there are just a huge number of applications that we can think of in microstructural science. I show a list on the left and a bunch of sort of snapshots or cartoons on the right. They range in everything from search, sort, classification, those sort of basic machine learning tasks, right through to specification and qualification, detection of rare events or outlier events, autonomous analysis, characterization methods, instance generation. We use generative methods, especially to create data sets for analysis or simulation, processing structure property connections, the fundamental task of material science, and so on and so on. And so there are just a huge number of areas where we can contribute if we can come up with successful methods. So let's talk about what those methods involve. I think that I will not surprise anyone when I say that there are two components for deep learning models for image data. The first component is the model itself. And typically the model is somehow based on a convolutional neural network. That's when we're dealing with image-based data. That still is gold standard. Now, there's all kinds of architectures, and some of those architectures perhaps even push the definition of a CNN. But bear with me. We know somewhere in the pipeline, we're going to have some kind of convolutional method that convolves across the image and turns the image into some kind of feature vector, something that tells us digitally the content of the image. So that's the first component. And then the second component is you have to give it images to train it, right? And that's typically a big data problem. ImageNet is one of the standard methods, one of the standard data sets that are used to train the various kinds of deep learning based vision systems. And ImageNet is a data set with millions of natural images that are used in this training. When you have those two pieces and you put them together properly, and we'll talk about some specific instances of that later, but you can do all kinds of things with images, right? You can find visual similarity. You can do classification. You can look at the picture of the kitten and say it's a kitten. You can do semantic segmentation. That is, you can find the pixels that belong to the kitten. You can do object detection or instance segmentation, where you find objects or even segment them out of images. And then you can do all kinds of image manipulation, generation in paintings, super resolution, style transfer, which, and so on. All these ways of taking the images and doing something with them. Now, we in materials science would love to do many of these tasks, but we have a problem. Our data set isn't typically large compared to something like ImageNet. And so the standard for dealing with smaller data sets is to take advantage of systems that have learned on the big data sets and do transfer learning. So for instance, with our CNN-based feature vector generator, we would use a CNN that had been trained on a large data set, say of natural images like the ImageNet data set. And then we would use the learned parameters that are already there to create our image representations. We may retrain only the final machine learning layers, for example. And with that, we can take rather small data sets, as we had here, a small data set of a few tens of images overall of powder materials, and do the kinds of fundamental image tasks that we do with the big learning systems, including classification, segmentation, object detection, instance segmentation, and so on. So here are a few examples of transfer learning. This is for segmentation. We, in this case, used VGG16 and as our representation, used it in a UNet for segmentation. And we used it pre-trained on ImageNet, but then retrained the last few layers on our own data set of ultra-high carbon steel micrographs. And we were able to train a segmenter to segment the multi-component microstructures. And this was actually a 5-component segmentation, a very tricky one, because if you see the darkest blue material, or I'm sorry, the medium blue is a network carbide, and the darkest blue surrounding that network carbide is truly a judgment call. That is the depleted zone. It's the ferrite matrix depleted zone, and it's considered separate from the ferrite matrix in the spheroidite zone, which is the aqua blue and yellow with yellow speckles. And so the system was able even to reproduce the rather subtle difference between the depleted zone and the ferrite that exists between the spheroidite particles. Here's another example for classification. This is classifying carbon nanotube aerosol particulates. These are TEM images, and these were taken at NIOSH. You know NIOSH, the N95 mask place. That's a government lab that their job is to deal with particulates in the workplace, hence the focus on masks. Well, carbon nanotubes are known to be bad for your lungs, and so it's important to be able to detect them in the air and to understand which kinds of particles are better and worse. They have a classification system for those carbon nanotube particles, and we can use a computer vision system to accurately classify these particles by their class. And as you can see, if you look across the 4 classes I've shown you, the particles in each class, the images are very different from one another. So it's a pretty impressive accomplishment to be able to correctly bin images that have so much variation within each class. Finally, we can do some regression on our images because we have a mathematical representation for our images. And in this case, this is measuring grain size in images that have ambiguous or missing grain boundaries. And we see that the predicted and actual grain size are in good agreement. And so these are all enabled by transfer learning, that is using out-of-the-box pre-trained neural networks to create our image representation for doing machine learning-based tasks, and it works well. But we still need some training, we can't just take out of the box and apply to microstructure. We do have to optimize our system for the microstructural images, and that leads to a couple of questions. How many images do I need to do a retraining, a transfer learning, a retraining, and what makes a good image? And this is all motivated by the fact that our image data are often expensive in cost or or time, or are difficult to acquire. And so if I have a data set here of powder particle images, is the 20 that I show you here enough? Do I need more? Do I need better? And that's what I want to complete this talk by talking about. So let's consider a fundamental image analysis task, which is segmentation of images. And here I'll show you a few examples. This row is a low contrast segmentation. I say it's low contrast because this is one that's actually quite difficult for humans to do. We can't tell the difference between lath type bainite, which is shown in the purple here, and random bainite, which is the rest of the material. In fact, the graduate student, in order to do the ground truth segmentation, has to rely on EBSD data, that's electron backscatter diffraction data, in order to tell these two components apart. So what we want to do is take an original image, train it on some annotations, and get a machine learned solution that would be able to do this faster and less expensively. So the CNN here actually gets excellent results on the same segmentation. And that's a good result. That's the kind of result we've had ourselves on the back, but we're talking about data set size. So I want to mention that, let's see, I'll do this. That segmentation happened with only 4 annotated training images sent to the retraining in the transfer learning pipeline. So that's pretty data frugal. We only had to do 4 of those difficult low contrast annotations. The second row, the middle row of images, is that powder material data set that I've been telling you about a bit. This is a case where we wanted to do instant segmentation of the powders themselves, the powder particles. That is, we want to, for example, measure the particle size distribution. So we need to take this dense image on the left, which has overlapping particles, and turn it into an instant segmentation on the right, where each particle is separately taken out. The pixels that belong to each particle are identified with a unique particle. And again, we have annotations in the middle that the graduate student did with a stylus and a tablet. It was very tedious. There's several hundred particles per image, but having annotated only 4 training images, we were able to get the excellent instant segmentation results shown on the right. Again, data frugal. And at the bottom, multi-component segmentation. This is that 5-phase segmentation that I talked about before, the all-tricarbon steel database. We have SEM micrographs as shown on the left. The graduate student, again, with a stylus and tablet, annotated the middle image, and we were able to use transfer learning to train a system shown on the right to give a very good segmentation of this complex microstructure with 1 training image. So let's talk about how we might do that. Why can we get to 1 training image to train a good segmenter? And I think the reason we can is that convolutional neural networks machine learning systems based on convolutional neural network representations learn objects based on visual features, right? And in natural images, very often we have only 1 instance of the thing we care about. This happens to be my cat, Sahara. But we do have images, but my cat has features at various length scales. So we have to learn about ears and eyes and whiskers and tails. The field of view tends to be arbitrary because I'm always taking pictures of them from every point of view. And they're almost always oriented typically with gravity pointing down. That means if I want to be able to identify Sahara in an arbitrary image, I need many training images. many training images to capture the range of visual features and points of view, fields of view that we can expect in images of a cat. Fortunately, I have no problem with that in my household. Sahara is by far the most popular photographic subject. But on the other hand, microstructural images are data rich. The reason is we intend them to be. They are data. We are taking them not for our pleasure, but because we expect to find things out from them, extract information from them. And so we will typically take what we consider to be a representative image that will have many instances of the object that we're interested in. For instance, many instances of the spheroidal light particles shown in this image on the left. We will typically choose a characteristic length scale to capture what we consider the relevant sizes of things. Often we have a standard field of view. It's almost always the plan view. It's sometimes oriented and sometimes not. So whether our images are oriented depends a lot on what we're taking a picture of. But the point is there's a lot more information in this picture of spheroidite in a perlite matrix than there is in a single picture of my cat. There's multiple spheroidite particles, multiple perlite colonies. There's size information that's relevant. There's the standard field of view, and I can get a lot more information out of this than I can out of a typical natural image. So let's talk about what that means in terms of data set size. And we're going to now focus on the segmentation problem in the ultra-high carbon steel database as an example, because we happen to have 24 excellently annotated ground truth images to work with. Now, there's 1,700 micrographs in the data set as a whole, and it is publicly available, by the way, and published if you should be interested in playing with it yourself. 24 of those images have full annotations. So what my student Bo Lay did was he trained the segmentation pipeline on one image and then tested on the remaining 23. And he did that for all 24 of the images. So basically what we're going to look at is which images make good training images if I'm going to do one-shot training. The pipeline used UNet with a pre-trained VGG16 encoder. And you can read the parameters along the right side of this slide, the batch size. The data augmentation was used. We flipped, rotated, scaled, and so on to make our one image go as far as possible in terms of data. And we used atom optimization and so on. Train on one, evaluate on 23. So here's what we get. This is the IOU score for each of the training images labeled 0 through 23. And as you can see, there's a great difference in the IOU scores achieved by different individual training images. For example, if we train on image number 4, we get poor results, right? A low IOU, the lowest IOU score. It's intersection over union. If you look at this image number 4, you can see why. It doesn't have all of the components that we want to segment. It only has the spheroidite in the ferrite matrix. It doesn't have the network carbide. It doesn't have the depleted zones. It doesn't have that long skinny Wiedmann-Starten carbide. It's missing information. Not a surprise that it's a poor training image, even though it is a perfectly valid member of this data set. We get a better result with image number 21. Image number 21 does show all of the components of the system, the network carbide rising up the middle with its depleted zone around it, the spheroidite in ferrite matrix, and a few whiskers of the Wiedmann-Starten carbide. So it's a better image. It's not at the standard magnification, so that's an issue. The best image for IOU of the resulting segmentation is image number 3, and it has all of the relevant phases, and it has the standard magnification for this data set. And it also has these dark blobs. They're polishing artifacts. They're things we want to ignore in segmentation. They're meaningless. It's important, it turns out, to have them in our training image so we can learn to ignore them. And so this is the best image for training because it contains what we want to identify and what we want to ignore, to learn to ignore. Now, Bo then asked the question, do we have to look through all our images and try to guess which is the most representative in order to do one-shot learning? And of course, that's a silly and non-productive way to do it. Instead, Bo defined a metric, the AMRD metric, additively maximizing representativeness and diversity. So what it tries to do is find first the most representative image. It does so by creating a VLAD-based representation of each image and comparing pairwise similarity. It looks for the image that is pairwise most similar to all of the other images in our set. But what if you want to add a second image? You don't want to add the second image to also be as close as possible to the second closest possible to all the others, because it's probably very similar to your first image. You want your second training image to be as dissimilar as possible from the one you've already picked. And then outside of that, similar to or representative of the other samples. And so what we're looking for is a set of images that are most representative of all the images in our system, in our data set, but is different from each other as possible. And that's what this metric gives. When we apply this metric, you can see the representativeness AMRD metric on the bottom. Remember the test mean intersection over union is same data as before that I showed you for this set of training of one-shot training images. In this case, it's only representativeness that we're paying attention to because we are doing one-shot learning. The highest representativeness images are 2 and 7, and they correspond to very high MIOUs. Moderate representativeness, we would say, is image 8, and it corresponds to a moderate MIOU in the results. And the low representative, same image as before, that terrible spheroidite only image, again, is low representativeness and gives a poor result. So the representativeness metric seems to work. When we want to add the diversity in, we move towards the multi-image training set. And so we studied the MIOUs that we achieved with one-shot learning, 2, 4, 8, and 16-shot What you can see is the blue bars show the IOU, the goodness of segmentation for randomly picked single-shot learning or 2-shot learning or 4-shot learning. The peach bars give the learning achieved by the best 1, 2, 4, or 8-shot data sets based on the AMRD metrics of representativeness and diversity. And then the full training is the 16-shot, and it gives a baseline for how good we can get. What you'll see is if we carefully select our training images using the AMRD method, we get substantially improved performance, especially in the low data regime. And we, of course, increase our performance and plateau out at approximately the full accuracy, the full MIOU accuracy by the time we get to 8 images selected by the AMRD method. The other nice thing is AMRD avoids the accident of achieving a non-ideal case. For example, it's possible to pick some really bad sets of images to train from. AMRD keeps you from doing that. And we show on the right-hand side, of course, just examples of good and bad, or less good and more good segmentation from the random versus AMRD selected training. So this gives us an idea that we can train a really complex segmenter, for example, with a very few images. By the time we get to about 4 training images, we have almost maxed out the system, and we've certainly spent a lot less time annotating images as well as training the system as we would if we had to go to the 16 or more training image set. So here's some conclusions for data collection here. The question I always get is, how many images do I need? And the answer is, for segmentation, we can have excellent results with 1 image sometimes, or a few images. Classification typically takes more images, about 10 per class. Prediction, especially regression, asks for more images yet. And so the first thing you want to know when you're considering a data frugal pipeline is, what am I going to do with it? And based on that answer, you get a good idea of the number of images you need. And then what makes a good image? Well, the AMRD metric helps us understand that. We need our images to be data rich. That is, they should have many instances of all the features of interest, including they should be representative of the features you want to identify and the features you want to ignore. They should resolve the features of interest. It is good practice to standardize imaging conditions. It's not entirely necessary, but it does enable you to typically get away with a more data frugal set. And the last thing is that there should be interclass differences and intra-class homogeneity. In other words, the different classes should look different from each other. A human should be able to tell them apart. But within a class, the more similar the images are to each other, the better everything will work out. Now, it's not always possible to achieve all of these aspects, but they are ideals to shoot for. Now, I want to move on with the last 5 minutes of my talk to talk about an alternative approach to minimizing data annotation. And this is to minimize the annotation directly rather than minimize the number of annotated images. And specifically what I want to show you is what we can do with PixelPick. This is an active learning platform that learns from labeled pixels without requiring a full annotation of the image as a whole. What PixelPick does is it takes unlabeled micrographs, and the user, in the upper left here, and the user will label a few pixels for each image. The user can decide how many. Those pixels are sent into the PixelPick pipeline, which learns a model using the labeled pixels. Within that model, it has an uncertainty prediction for each of the pixels that it is predicted, and it samples some of the uncertain pixels and requests that the user update the labels of those pixels. Then it retrains the model, and that's a loop that continues. So it's an active learning system, and it queries the user for additional information as it needs it. This reduces annotation effort. We don't require the dense annotations, and it can be used interactively. One of the nice things is the hardest pixels for the humans to decide upon tend to be the ones that slow down the annotation process. It's really helpful to have PixelPick decide on what pixels need to be carefully scrutinized and which ones can be ignored. It really speeds up the flow. Here are on the left are the PixelPick results, again, for the ultra-high carbon steel data set. You can do either uncertainty-based sampling or random sampling. The uncertainty-based certainly outperforms the random sampling for any number of pixels that are chosen. I'll draw your attention to a couple things about this graph. First of all, is that the number of pixels, the number of labeled pixels per image tops off in this graph at 100. That is the largest runs we did. We only needed to identify which phase 100 pixels in each image, in each of the training images belong to. So that's a very small annotation burden. And in fact, we reached maximum performance by the time we'd labeled 40 or 50 pixels. So really decreases the annotation burden. However, the fully labeled system can achieve this dotted line level of accuracy on the segmentations. It still gives better results than PixelPick. And you can see that there are some problems. PixelPick is able to be confidently wrong about pixels. If you look at these red arrows on the top row, they're pointing towards some spheroidite that PixelPick incorrectly labels as network carbide. It's confident in that, though, because those show up as low uncertainty pixels, and so it can be confidently wrong. The other point is that the uncertainty-based sampling prefers the boundaries. That's not surprising. Those are the areas of greatest uncertainty in a segmentation, and those are the areas that always challenge annotation and segmentation. You can use the PixelPick in 3 scenarios that it's really useful for. That is rapid development of a good enough segmentation method from very little data. You can use it to produce pre-annotation masks that you can then tweak as the user to get a perfect ground truth. So you can correct the bits of errors that pixel pick leaves behind much more quickly than doing a full annotation mask. And you can refine the models for unseen data, and that's kind of nice too. So to compare the methods I've told you about, the data-frugal methods I've told you about, we start with the baseline, fully supervised, 16 images, 100% labeled. We get the best results, an MIOU of 82%. That's quite good on a complex segmentation like we've seen, but it takes at least 24 hours in annotation time, not to mention all the other time put into the learning system. If we go down to 4-shot learning, we chop our annotation time by a factor of 4. We don't lose much in MIOU, and we've only labeled 25% of our data. We can move all the way down to 1-shot learning. 1 image, 6% of our data is annotated, and it's still got a pretty good segmentation result. But if we move down to the pixel pick with 50 pixels per image, we've taken less than an hour to annotate everything we need to annotate, and we've maintained a accuracy very similar to what we had in the 1-shot or 2-shot learning. So it's up to the scientist to decide what the objectives are and what the resources are to put into it to achieving those objectives. So I'll put my conclusions up. How many images do I need? It depends, but it can be surprisingly small. What makes a good image? A representative image. And there's a bunch of axes to consider representativeness on. And most importantly, if we choose an optimal method, we can make the most of the least data, whether it's by selecting a small set of images to be the most representative and diverse images to minimize the number of annotated training images, or whether it's going down to a pixel-wise method to minimize our annotation time insofar as possible. With that, I'll thank group members and collaborators and take any questions if there's time. And I know that there are a couple questions in the chat. If the meeting chairs would like me to answer them now, I will, or if not, we can talk about them in the panel discussion.
Thank you, Liz. It was very interesting presentation. We have time for 1, maybe 2 questions. And there'll be more time during panel discussion.
Well, let me address Amanda's question in the chat. She asks, do the rules of thumb on slide 18, which I'll try to go to here, still apply if the problem is more of an anomaly detection? That is, say, a defect localization, or should further representations be required? Let me get up to that slide here. And that's asking how many images would you need for an anomaly detection. And that's a great question, Amanda, and one we work on, one that is very tricky. What I would say is typically you need, in anomaly detection, the challenge is getting enough images of the anomaly, right? And typically, for instance, in a quality control where you're looking for defects, you have lots of images of good material because you're pretty good at making whatever you make. You have few images of defects, and that tends to be the bottleneck. That can be solved 2 ways: getting more images of defects, and it need not be a ton of images. Again, you can go back to these data-frugal methods, but you do need enough. And/or the second option is to use generative methods to supplement your anomaly data. And that is a method I know that some collaborators of mine at Saarland University are working on right now, for example, and I'm sure others are as well. That's the idea of being able to generate images that will help your training be more effective. And you'll be generating images from images that you already have. So that's two ways to go towards that. And with that, I think my time is up.
So time for 1 question.
Okay.
Okay. So then let's move to the next talk. I would like to introduce Luther McDonald with intriguing talk about nuclear forensics. And Luther is an associate professor in the Department of Civil and Environmental Engineering and the Nuclear Engineering program at the University of Utah. He joined the University of Utah in January 2014 and has led the development of radiochemistry laboratory, mentoring over 40 students and managing research projects from NEU, DATRA, NNSA, and the Department of Homeland Security, including Department of Homeland Security Nuclear Forensics at the graduate summer schools in 2016 and 17. Before joining the University of Utah, Luther performed a postdoctoral fellowship at Pacific Northwest National Laboratory in National Technical Nuclear Forensics, worked as a visiting scientist at the Commissariat G Atomic in Saclay, France. He served as the elected secretary of the American Chemical Society's Division of Nuclear Chemistry and Technology from 2013 up to 2016 and was named one of Forbes 30 under 30 in science in 2017. Welcome.
Wow, thank you, Alexi. That was quite the introduction. Also, thank you to Elizabeth for that first talk. It was actually the perfect setup for what I'm about to talk about, and we didn't even plan that. So I think maybe the organizers planned that, and that was really quite lovely. I appreciate that. Before I dive in with all of this, I like to acknowledge that this has really been a team effort. There's been a lot of people involved in this project for the past decade, and I'm just the one that's up here presenting it, but I certainly was not the one who did the majority of this work. I also would like to emphasize that I am a chemist by training. I do not do machine learning or any type of computational analysis. I am someone that is on heavy experimental side from making the samples and collecting these images. But really where I think they asked me to come and talk about this today is that my work has only been successful because of collaborations with people who can do the image analysis and the machine learning. And one of them is in the audience today, Tolga Tastison. I'm actually quite grateful he's in the audience today because I'm going to talk about a lot of the collaborations that we've had throughout the past several years. So before I dive into this, I thought maybe I should give a little introduction on what is nuclear forensics and why are we interested in some of this work. So the International Atomic Energy Agency, or the IAEA, defines nuclear forensics as the examination of nuclear or other radioactive materials using analytical techniques to determine the origin and history of that material. So as kind of a simple overview, on the right-hand side of this image over here, we're looking at our nuclear fuel cycle, which goes from everything from the mining operation of how do you get your fuel to ultimately your power production, which happens in a nuclear reactor. But there's a lot of stages that go in between that, and then a lot of stages that happen on the back end of that. So from a nuclear forensics perspective, we really want to understand the origin or the history of all of these different stages. So the one that I'm going to focus on specifically is actually this conversion stage right here in the middle. And what are all the different production histories that go about within that single stage, and can we identify the history of a sample that has been interdicted or found during processing of that specific stage? And why do we need nuclear forensics? It might be obvious to some people, it may not be obvious to others. The IAEA has an incident and trafficking database in which they document all incidences in which nuclear materials have been reported outside of regulatory control. And since 1993, there's been a little over 4,000 of those incidences. So it is important that we have an ability to identify the history and origin of these materials. So morphology specifically, or the microstructure of these nuclear materials, its main role in nuclear forensics is for identifying that processing history. So if you look at what we consider to be traditional signatures in nuclear forensics, that might be something like isotope ratios, or what is the chemical composition of that material. That will tell you a specific stage that you might be in the fuel cycle. But understanding specific processing conditions can help you identify even more variables within a single stage of that fuel cycle. So what is morphology? From a simple perspective, we think about it as the microstructure of those materials. So Elizabeth just showed us very beautiful microscopy images where all of the particles had really nice defined boundaries to them. Within some of these uranium materials, we can sometimes get images that look like that, but oftentimes our images are, I would say, a little bit cloudier because we're looking at very small particles, or we have a lot of overlap in the particle structures themselves. But at the end of the day, let's say we take 5 different industrial processes and we can vary the chemistry within those processes. So this conversion chemistry. From a chemist's perspective, the chemistry itself is relatively easy to vary, but at the end of the day, you get the exact same final product, which is uranium dioxide. So that will tell you what that final product was, but it doesn't tell you how did we exactly get to that final product. So that's where we can use this morphology and say, okay, well, the size and shape of these uranium dioxide particles varies based off of this specific chemical process that was used to actually make them. So when we set about to develop morphology as a fingerprint in nuclear forensics, the first stage of it was to establish a baseline morphology in which we just said, okay, let's take 5 different commercial production routes, let's replicate them in the laboratory, and let's just see what the microstructure of those particles actually looks like. From there, we then had to evaluate how easy is it for that microstructure to change. If you have a material that has more impurities in it, what does that do? If you change some of the chemical conditions in making it, what does that do? The next stage has been to look at how stable is that fingerprint over time. A lot of times these materials might be several years old. They could even be decades old. How are they aging or evolving over that time period? And then the last one, this is kind of the holy grail that we would love to get to, is can you generate these predictive models? So do you have to have training data for every possible scenario of what that morphology or microstructure might look like? Or can we eventually learn enough that we can predict, hey, these different chemical processing conditions would make this specific microstructure at the end of the day? This is a really hard one. This is something that will probably be my entire career that we work towards, but the others we're making pretty good progress on, and I'll share some of the results from that. So within the first stage, it really was to establish that baseline morphology. So what I'm showing here on the right are 5 different uranium materials from 5 different production routes. So this ADU stands for ammonium diuranate, AUC is ammonium uranyl carbonate, magnesium diuranate, sodium diuranate, and then uranyl peroxide. From all of these different materials, you can make uranium trioxide, UO3. And I talk about making uranium like baking cookies in an oven. UO3 you make by baking at a relatively low temperature in the oven. If you bake at a higher temperature in the oven, you'll remove more of the oxygen and get down to U3O8. Baking at a higher temperature doesn't remove more oxygen to get to UO2, but if you add hydrogen gas or reducing atmosphere, that will get you down to this UO2 product. So all 3 of these, same starting material, different end product based off of how it was physically made. And then coming down these columns here, we're looking at different chemical processes that were used to make them. So visually, as someone looking at these, the great news is that I think they all look very different. The challenge becomes, how do you prove that they are different? Because in a nuclear forensics setting, we can't just go based off of how we feel. You have to be able to quantifiably prove that different materials are indeed actually different. So when we looked at quantifying this particle morphology, there were a couple unique features that we started to look at. So one was these particle agglomeration patterns, which was typically observed at a lower magnification. Generally, we're observing this somewhere around 10,000 to 25,000 magnification within a scanning electron microscope. If you look at these, you see that this image here on the top left has a lot more uniformity in how the particles are clustered about, whereas on the right, we see a lot more large clumps or agglomerates that are forming within these particles in terms of their agglomeration. However, if we were to look at these exact same materials, but at a high magnification, now 100,000 magnification, we see a lot less, or we see a lot more similarity between these materials because we can no longer really clearly see those agglomeration patterns. But what we're starting to see is maybe a little bit more of the edges of the discrete particles within these different materials. So in this instance, this is where if we could segment these individual particles, we could describe perhaps the size and shape of the particles and use that to quantify differences between these production routes. And there are 4 approaches that we have used for trying to quantify this morphology. One of them is through particle segmentation, and we've done this through collaboration with Los Alamos National Laboratory, so Kari Sintz and Reed Porter, and they have developed the MAMA software. It stands for Morphological Analysis of Materials. It's based off of a water shedding algorithm for being able to draw boundaries around these discrete particles. Beyond that, we have also looked at computer vision techniques. So this is really where we get into the supervised machine learning, the unsupervised machine learning, and then kind of combining the first three together. Is there an avenue for human in the loop machine learning, which Elizabeth actually showed a lot of really great progress in which they learned what a human was segmenting in that first talk of the day. So just to give an example of what segmentation looks like using the MAMA software, on this top left would be an example image coming in. A graduate student would then go through this image particle by particle. And for us, we chose to segment only the particles that had clearly defined boundaries to them. And that's because we were trying to look at statistical attributes about them, such as the size and the shape. But if there was overlap in the particles, you couldn't have confidence in what the size and shape of this individual particle was, because you couldn't get its boundaries as it was overlapped by another. So in the end, you would see a particle like this, which had very clearly defined edges, that would be segmented so that on your final segmentation output, you would have something that looked like this. It looks beautiful, but at the end of the day, that's incredibly time intensive. It might take an individual person somewhere between 30 minutes to an hour, depending on how clearly defined the particles were within that given image. Nonetheless, if you have an army of a workforce that can go through and do lots and lots of these images, you can get these statistical attributes from them from that MAMA software. So we're looking at two different attributes, one being an attribute based off of the size of the particle or the pixel area, and another one based off of the shape of the particle or the ellipse aspect ratio. In this example, we could see that uranium oxide particles produced from ADU had very, very small particles resulting from them, whereas this other route, AUC, resulted in very large particles. That's very easy to tell that they are statistically different. However, we could look at, say, these two in the middle, AUC here and MDU here, and say, well, they have the exact same pixel area or size particle, but the shape of them through the ellipse aspect ratio would be statistically different. So by combining a shape and a size attribute, we could have 99% confidence in identifying that these materials came from different production routes. Of course, the challenge becomes is we were able to do that segmentation on maybe 50 to 100 images at the end of the day. But we really want to build up very large image databases so that we can really encompass the entire range of what the morphology of these particles could look like. So throughout a 5 or 6 year period, my laboratory focused on making these materials and then gathering the images of these materials to where we got up to about 20,000 images of these uranium oxide particles. We then really started heavily collaborating with Tolga Tassisen, and his group focused on using convolutional neural networks. And one of the first networks that we focused on was taking input from different magnifications so that we could capture those different agglomerations of the particles, as well as the different sizes and shapes of the particles. And by training on all of those different magnifications, we could get a prediction or an output of what an unknown image would look like with a very high classification accuracy. And so we were getting well above 95% classification accuracy when looking at these 5 production routes in any of these different new oxides here, which had been produced. So really quite wonderful and fun work at the end of the day. The next big question became, okay, but Luther, all of your images were of perfect and pristine materials. In the real world, in a true unknown setting, the material may not be that perfect. There may be a lot of impurities that are there. It may have aged quite a bit. It may have gone to an SEM operator who wasn't trained as well as your students. And so just the quality of the image that you have coming in may not look as good. So with that, we wanted to start testing out what are the limits of where do these different models fail. And so we started looking at out of distribution data. And so this is where we started looking at, okay, what if our images were captured at different magnifications? What if they were captured on different scanning electron microscopes by different users? How well can our existing models generalize to these unseen out of distribution problems, which are more likely to be encountered in the real world? And this is really where we had that great synergy between the experimentalists and those who specialized in computer vision, and which in working together, they were able to say, hey, these are areas where you need to get more images if you want to be able to do good classification. And we were able to go back into the laboratory setting, make those materials, and get that type of data. So I'll give you a few examples of that now. On the left would be how we started out this out of distribution data problem, in which we had these really nice, pristine materials which went in for our training data. And then as our out of distribution data set, we basically took other images that had been captured that weren't nearly as perfect as those. And so these might be images captured at a different scale, so different magnification. They might be materials that had impurities in them, materials that had aged, or materials that had different solution chemistries affiliated with them. Once again, visually, we can look at these and say, okay, well, we see some differences, but we don't have enough of this for training data initially. So we just have to see how well do we do on this out of distribution data. The other thing that we really wanted to evaluate is how will we know when using these convolutional neural networks or supervised machine learning if we're getting an incorrect prediction associated with it? Because it has to give an output for it, and that output is based off of our training data, but it could be very confident in that output, but very wrong in that output as well. And I would say this is definitely not an area I'm a specialist in, and it's an area that we need a lot more research because it's very important from a nuclear forensic setting. The way that we went about doing this was looking at the information entropy in the predictions that were made from the neural networks. Now, again, coming at this from a chemist perspective, I think about what is entropy in a system, and we think about that as the amount of disorder that exists within a system. The more disorder that you have within that system, the less confident you are in the output of that answer. The less disorder you have, the more confident you are. So in our correct prediction, we really want a very low entropy because that means we're quite confident in that. And if we look at just our holdout set, so this would be, we used a certain amount of the images for training and then a certain amount of the images for testing, we had a very low amount of entropy, a very high classification prediction. That means that we are very confident in that analysis, which was great. That's where we want to be. When an image was incorrectly classified, it had a high amount of entropy in that system, which was also good because that means that we really weren't confident in that incorrect classification. The challenge became is that we had very few data sets that showed up in this top left quadrant, which is really not too unsurprising because our training data was too perfect. We didn't have enough of those variables in the training data, such as different SEMs, which sounds like such a simple thing. It's a different electron microscope. Why, if you have, the same imaging settings on it, why would the images look that different that it would throw off your classification accuracy? But the reality is that it did. And then there are others, if we collected at different magnifications, if we had variations in the chemistry, which we expected, would make challenges within our classification. So a few of the things that we learned, if a sample was relatively young and it had been stored in pretty good conditions, the aging of that material didn't really impact our ability to do classification on it. If we changed just some of the solution chemistry variables, it didn't have that big of an impact on our classification either. Neither did some of the basic electron microscopy image settings. However, some of the other ones had much bigger impacts on our ability to classify that out of distribution data. One of them being what was the magnification that the image was actually taken at. If we tried to take an image that was at a low magnification, say 500 or 1,000 magnification, and compare it to something, our database of 50 and 100,000, that created a lot of challenges affiliated with it. If a material had been aged in pretty extreme conditions, it would look a lot different than the training data, and then impurities as well. The good news is that then led into the morphology multi-laboratory project, which expanded that collaboration between the experimentalist and the data scientists. And this project is being led by Los Alamos National Laboratory, but it now takes these different components and really combines them together so that we can say, okay, let's put people who are experts in designing the experiments that should be done with those of us that go and actually make these materials in the laboratory and get the images. We then have to feed that into our statisticians who can do data analytics and our experts in image classification and machine learning that can do model validation. Ultimately, all of this will hopefully go into some type of software package that could be used at the end of the day for some type of unknown image. So from the experimental perspective, we kind of had two goals where we said, okay, we want to know roughly what are these blue rectangular boxes up here? What was that chemical production route? And then can we start getting into specific details of those materials? No longer just, hey, this was AUC to UO3, but this was AUC to UO3 and it had a lot of impurities in it. So can we go to those types of higher fidelity? And this really gets into that second stage of establishing a signature or going beyond what is that baseline morphology. So I told you with out of distribution data, we found out that impurities ended up having a pretty major impact on our ability to do classification or identify the morphology of that. So we went through as experimentalists and said, okay, well, we can add in impurities. Generally, we like to work with ultra high purity materials, but it's not too hard to introduce an impurity in that system. And for us specifically, we worked with a fluorine-based impurity within these materials. This is where we then went in with the electron microscopy and said, okay, traditionally we'd work with only secondary electron images. If we work with backscatter electron images, we can see a contrast based off of different elemental compositions within those materials. And by doing that, we could see regions and highlight, hey, this is exactly where the fluorine impurity is within that material. And this is where all of the pure uranium material is within it as well. Again, going through and doing this with a lot of training data for a lot of impurity, we can start building up databases for learning what do these different impurities look like within these different materials. We then started artificially aging as well, not artificially aging them, intentionally aging them. So we would take environmental chambers and we would take this pristine starting material and we would say, okay, it's going to go in an atmospheric chamber, which will undergo diel cycling. So 10 degrees Celsius, 10% relative humidity, up to 30 degrees Celsius and 75% relative humidity. And then we would look at these materials at different time intervals coming out of them so that we could start to, again, build up training data that understands this is what this material looks like as it's going to age over time. And then one of the easier ones for us to address was actually differences in how the SEM images were collected. And so we found different scanning electron microscopes available on campus at the University of Utah. And we said, okay, well, we can take all of the existing materials that we have, send users to these different electron microscopes and get images of the exact same materials on those different electron microscopes so that we can learn what do these differences look like at the end of the day. And while I was talking, Kwong Lee actually just came into the room and he was the one who took all of this training data that we generated and was able to basically publish this paper on improving robustness when looking at these different electron microscopy images of these uranium oxides. So why, at the end of the day, was it important for us to standardize all of this different collection and images that we are looking at? Well, that's really because we want to be able to expand our network of where are these electron microscopy images coming from, and we want to be able to work with other partners besides just what the University of Utah is collecting. And one of the big questions with morphology has always been, you know, at my laboratory at Utah, we're making these on a relatively small scale, a few grams at a time. But in industrial processing, you're working with metric tons of material at a time. Will the morphology of this material still look the same? This is where I was fortunate enough a couple of years ago to go on a sabbatical to Australia. And the reason I went to Australia is they're the third largest producer of uranium in the world. And while working at the Australian Nuclear Science and Technology Organization, there were 3 different U3O8 samples produced from industrial mines that we had access to. So one from Olympic Dam, which is down here in the South Central Australia. It's one of the largest uranium deposits in the world. The Ranger mine, which is also a very southern mine, and then the Beverly mine, which is an in situ mine for recovering that uranium. So if we were to compare the Australian samples to the Utah samples, there were very few things that were actually identical about them. So one was that they were both found from ammonium diurenate. That was a similarity. We both did our calcinations at 800 degrees Celsius. That's baking our cookies in the oven. Very high temperature for actual cookies, but that's what it takes for uranium. And then there were a lot of variables between how Australia produced their samples and how we produced them on that very small scale. So once again, dramatic differences in these materials, but we're never going to be able to be identical in what we're doing on the lab scale to what's done on an industry. So having that generalizability in our networks is really quite important if we want to be able to apply this in a forensic setting. So I'm going to conclude this just by showing you some of the images that we got from Australia relative to some of the materials that were produced at Utah. On top is U308 that came from the Ranger mine. On the right is U308 that came from the Olympic Dam mine. And then these are different productions that we did of ammonium diurenate down to U308 as well. All of these images are slightly different sizes just to adjust the scale bars in them to be equal across the different images. This is a great example of these were collected on different scanning electron microscopes by different users. And so the uniformity in them will never be perfect. But that is really why we've been working with experts in image analysis and machine learning to focus on this generalizability, because standardization will never be perfect going across institutions or scales at the end of the day. So in summary, what we've been able to do with morphology is show that uranium oxides do have unique morphologies based off of the chemical processing that was used to make them. That's really important because that means we can use those differences, if we can quantify it, to identify how different uranium materials were made. None of this would be possible without collaborations between the experimentalists and those who are experts in actually processing the images at the end of the day. If it was just my group going and collecting the images, we would look for the pretty and the unique particles, and that's all we would get. And we'd get maybe 5 or 10 images and call it good. For Elizabeth, that actually was good enough. And so I was quite intrigued by that. For us, we've needed thousands of images to be able to show some success with the machine learning aspects of them. We do know the different variables that will alter those morphologies, such as extreme aging of the samples, adding impurities into the samples, but those are challenges that we can overcome by going back and getting more data at the end of the day. Getting more data is expensive, so if we could get to that holy grail of predicting what would the microstructure look like without us having to physically make the materials, that would be ideal. But like I said, that will be a long-term objective at the end of the day. The best case scenario would be to, again, help standardize how these images are collected, because we do know there are some simple variables that can be overcome, such as what's the magnification that the image is collected at. That seems like such a simple thing, but it actually has a pretty big impact in actually quantifying those materials and having a high classification accuracy at the end of the day. So I'll conclude it by once again thanking all of the partners who helped us collect this material, make these materials, and analyze these materials, as well as the facilities who have enabled us to gather these electron microscopy images so that we could then start building these different models at the end of the day. And with that, I'm happy to take any questions. Thank you.
Do we have questions online?
No, why don't we go?
Okay, yeah, go ahead.
Given that, great talk by the way, given that your goal is to classify nuclear materials, I assume that part of the goal will be to classify them from sources that, potentially from rogue foreign actors, where you may not be able to get images as part of the training data set. So how well do you think your model would respond in that case?
That's a great question. And fortunately, that goes beyond me, because at the university, my goal is really just to make these materials and say, can we classify them based off of different chemical processing conditions? At the end of the day, how these get used is up to other people beyond my knowledge.
I was curious about the process to, like, if you have a new enrichment process, never been done before, totally innovative, you go to add, you would need some training data. So what's the procedure for collecting that? What data would you think is like absolutely necessary? And then did you guys measure like the extent to which maybe these general characteristics such as aging or impurities, like you could add a minimal set of the new process, just like perfect pictures. Does it do better on aging than if you don't have any aging data of that specific process, but because you have aging from the other, is there any transfer?
Absolutely. So that's a great question. I guess I'll answer it in a couple different parts. So one would be, if we were to get a sample that was truly different than anything we've ever trained on, we would love our network to be able to tell us that.
Right.
Because that by itself would be very powerful, in which we go, hey, we have all of this training data. It is not a match for any of it. And so that's one way of identifying this might be something new that we don't even know about yet. Whereas right now, we actually aren't very good at just that task by itself, because it'll classify it, and then you have to figure out how much uncertainty was there in that classification. Should we actually trust that classification that it was given? In terms of adding data in, training these models, and correct me if I'm wrong, Tolga, is actually relatively quickly. It doesn't take that long to train them at the end of the day. So if we were to gather new data, or we were to say, hey, we really need aging data on this specific set of parameters, adding that into the model isn't something that's going to take days or weeks. It's something that could be done within hours at the end of the
Well, not
day.
the training, but the labeling is probably.
Well,
part of
so
this.
that's where, if we're doing segmentation, the labeling is very labor intensive, because a human has to go in and actually identify what those unique features are. If we're not doing segmentation, then it's really quite quick.
But you're just classifying.
Just classifying, yes.
And you already get.
Yeah, thank you. I had a question. You had mentioned earlier about impurities potentially changing the final product. So I'm wondering that, have you looked at the geology aspect? If there are impurities in the beginning of the process, even if they're baked off during the process, maybe that's going to result in different products from different areas of the world. Is that something you've examined at all?
Absolutely. And so there's been a lot of research looking at rare earth element patterns. And so if you're not a geologist or a geochemist, that probably means nothing to you. But all of those elements that go in your batteries at the end of the day, and there's been a lot of talk about rare earth elements, they come in very unique patterns in different uranium ores. And so those have been measured. And based off of the patterns of those rare earth elements, they can identify a specific ore that a material came from. Now, in terms of that's impact on the morphology, those are at something like the part per billion or part per trillion level when they're left over in the uranium product. So from a morphology perspective, they really don't have an impact because they're at ultra-trace concentrations. Where we've seen impacts on the morphology is when you have an impurity that's at 0.1 weight percent or a half a weight percent. And those impurities generally come from the chemical processing that was done, meaning someone added an impurity into the sample just to make that next stage of it.
Thank you.
Great question.
Okay, yeah, I thought that was a great talk. I think pointing out like the importance of generalizability across instruments and across like measurement techniques is really important for material science. I was curious on your thoughts on how we could achieve that. Are there any strategies beyond just like taking data across all these instruments, or
Sure, I
anything
mean,
else?
from an experimentalist, I go, oh, we'll just get data on everything. But that's also a very expensive approach to do that. And so I think one area that would be really interesting is to create a series of standards where, basically we could say, hey, here's a UO2 and it has this specific morphology. And here's another UO2 and it has this specific morphology. And if you have those standards and they go out to every laboratory, no matter who measures them, you should get the exact same circularity and the exact same pixel area on that particle because it's a standard material. And so that, I think, then could act as a normalization for these different instruments and how the image or the quality of the image might look coming from those different operators or those different manufacturers at the end of the day. But that said, those standards don't exist right now. And so that would be a whole new area of research to develop those standards to use. I believe we might be able to capitalize on other fields so that have created other standards for their industries. So there might be like a standard for steel or something like that. That wouldn't be a great one because it's not a powdered material, but you kind of get where I go, I guess. Sure.
Thank you very much for the talks. Really, I have a doubt, and it's I think that you use like two models for this. It's like first one is a segmentation model where you extract like characteristics of the sample.
Sure.
I have a question for that. That is,
Sure.
How would it is to segment things that have complete boundaries to those that are more or less could be boundaries or not? It is a difficult task. And
Yes.
I suppose that then you have a second model that is the one that is tries to classify the samples. That second model is based also on images, or you extract the characteristics through the segmentation and then use like a numerical model to make the classification.
Yes, so I'll answer the first one first, and then I'll go into the second one, if that's okay for you. So in terms of segmentation here, how do you define where the boundaries are, or what is a particle? That's a great one. That actually introduces a lot of human bias, because what I define as a particle may not be what you define as a particle. So when we did our statistical analysis here to get to these means and these standard deviations on them, we had at least 10 different people doing the segmentation. That way we would capture that diversity of what different people are considering a particle at the end of the day. And that was really our hope of just trying to capture how much variability will be there. And you could still have more variability, but we looked at it and said, okay, if we have 10 people, that's pretty good at capturing a pretty wide array of what diversity will be in defining what a particle is. There are tools that you could remove the human from this process, so such as segment anything, which has come out at the end of the day. That would be a way of potentially applying segmentation, but then you have to go, okay, you get a circularity or a pixel area, and we're saying that's the pixel area of a particle, but is it what a human would define as a particle, or is it what segment anything defined as a particle? So that's kind of the two avenues for the segmentation. Now, we have done one project, Tolga and Kwong as well did this one, in which they did use a convolutional neural network to learn what a human had segmented. And so they basically took all of our masked, so this one over here, and our unmasked images and learned what those 10 different people chose to do as segmentation. And then they applied it on new images that had not been segmented before and found that it did draw very similar boundaries based off of learning what a human had done for segmentation. The challenge becomes is that can apply if the size and shape of the particles are the same or very similar. If you have a very different looking size or shape particle, that does not work. You'd have to have new training data for that new size and shape of the particle. So that became labor intensive and we couldn't generate all of that data. The second approach is where there is no segmentation or no human interaction being done with these images whatsoever. So in fact, the images as we supply them to Tolga and his team would be 1024 by 1024 in terms of pixel area. And when they're using this ResNet network, they would be taking 256 by 256 crops, and they would do random cropping, they would rotate the crops, they would do all of those different features on them basically to get every point of view they could from that single image. And so within that, and I'll turn to Tolga and Kwong here because I'm speaking as a computational person and I don't really know what I'm saying. The images are just fed in and they're learning them in a traditional convolutional neural network setting. So pixel by pixel comparisons looking at them, but there's no other additional variations that we're doing to them. Does that answer your question? Okay.
I was curious about the classification, like the class list, I guess is what we call it. And then the data set, like how deep did you go into the metadata? Like, yeah, it's the process one versus process two, but do you have data that would be like process one from lab one, process one, you know, that like,
yeah.
I guess how deep does it go?
Yeah, absolutely. So that is a big part of what we're doing here. So the initial stage was just this blue up here, which was the generic classification. And then the second stage of that is going into variations within that individual classification stream. So saying, okay, we did different variations in the chemistry of them, variations in the temperature of them, variations in the stir rate of them, all of those different variables. So that is something that we are working towards.
Stir. That sounds like a change to the process.
It's a physical change to the process. So literally just the rate at which you're mixing the material, the chemicals as they're being combined together. Something sounds so simple and it can change the morphology. Yeah.
Just don't know anything.
No worries. They're great questions. No, I love answering them.
So I would like to make a comment about how to deal with different levels of magnifications. The same problem is faced by remote sensing community, where you collect huge sets of images at different resolutions. Those resolutions are known as ground sampling distance. So one of recent approaches is to embed GSD when it's available during training of neural networks. And it was shown that later on after training, even when you don't have GSD or magnification, let's say, information, network can still figure out what magnification is used to collect imagery and can produce much more accurate results.
Oh.
And one of the approaches is known as scale MAE. MAE stands for masked out encoder. And the other one, actually, both recent ones. The other one doesn't use GSD directly. It's known as cross-scale MAE. So it may be worth taking a look at some of techniques in like community from the neighboring room.
Oh, sure. Thank you, Alexei. Thank you all for your time.
Thank you. So our next presenter will be given a presentation online, remotely, and we are tuning to oral presentation, 10 minutes, 10 minutes, and probably one question afterwards, and then we'll go to the poster session.
Right, so I believe our next speaker is Takming, if you want to share your screen. And you are currently muted, so we can't hear you.
Can you hear me?
Yes.
Great. Okay. So, good morning. I'm Takming, coming from Helmholtz and Tomperian in Germany. Unfortunately, this year I cannot join your discussion in Seattle, so I can only give an online talk about our latest work on volumetric optical flow network for digital volume combinations. So, to begin with, let me introduce you to our studies of biodegradable implants. So in recent years, using biodegradable materials as bone implants have drawn attention to the biomedical research areas because this can avoid a secondary surgery to reduce patients' pain, surgery risks, or medical costs. So in our research group, we're interested in the implant stability during in vivo degradations and bone healing. So we conduct some push-out tests using single-strand radiations, computed tomography imaging beamlines operating at DC here in Hamburg. So as the tomogram shown in these figures, by a proper processing pipeline such as flat field corrections, artifacts removal, and tomography reconstructions, the resultant 3D volume has a voxel size of 5 micrometer using attenuation's contrast technique. And in order to track the bone deformations, we estimate the local 3D displacement field between consecutive volumes using digital volume correlations. As shown in the figures in the left, we can calculate the strain of the bone implant materials by the estimated displacement field using different mechanical force loading. Now, interestingly, researchers in recent years started to apply optical flow methods to DVC because of their similarity in estimating the deformation vector fields. However, utilizing state-of-the-art optical flow networks for DVC is still very new to the material science community. Although optical flow networks it can obtain better results than classical iterative approaches. This is particularly due to the high requirements of GPU memories for volumetric data. So therefore, we extend one of the cutting-edge optical flow networks with current all-pairs field transport, or a well-known, we call it RAFT, into the volumetric data for DVC using the supervised learning approach. We generate several types of synthetic displacement fields and applied to the measured micro-CT data for training, validation, and testing. And then we compare our approach to one of the latest iterative approaches to the synthetic and measured dataset. So now let me briefly introduce about our approach, volumetric raft or fold raft in a top-down manner using this block diagram. So our approach starts with patching the full volume from 1K by 1K by 1K voxels to volumetric patches in 80 by 80 by 60 voxels. These patches are passing through feature encoders to extract volumetric features where we can find the blue blocks in the figures. So by computing the dot products of these features, we construct a 6D correlations matrix that represents the similarity of these extracted features as shown in the yellow blocks in this figure. And by utilizing a multi-scale pyramid, we generate feature maps from the correlation matrix by these correlation lookup operators in the orange color. And finally, these gray color 3D recurrent update operators predict a sequence of displacement fields based on these correlation feature maps. And in this work, we train the networks to minimize the L1 distance of the predicted and the ground truth fields based on the predefined foreground segmentation mask. So the next question will be how this network is trained. So we prepared 39 measured micro-CT volumes as the reference volumes V0, which consists of bone plus screw samples using titanium magnesium alloys and also a polymer. We generate 5 classes of synthetic 3D displacement fields, as shown on the left-hand side in the figure. And by selecting parameters such as the maximum amplitude and frequency, we obtained 23 sets of displacement fields. And finally, by applying random parameter generations and also data segment augmentations, we simulate more than 800 fields for each CT volumes. And then we apply all these synthetic fields to the measured CT volumes by volume warping and generate the corresponding deformed volumes V1. And therefore, we have in total around 900 synthetic data sets for training and validations, where we exclude 69 of them for testing. So in these figures, we can compare the predictions to the ground truth in a qualitative approach, where we can see the field in X, Y, Z directions on the first, second, and last rows, respectively. And while we comparing to the state-of-art iterative approach, MBS optical flow in the middle column, middle 2 columns, we can observe that the result of our network generally resembles the star displacement field shown in the figures. However, it can also obtain block-based artifacts near the edge of homogeneous regions. This is due to the patch-based inference methods. And this is a limitation to the current approach, and we are looking for solutions for these kind of artifacts. And then we further evaluate the accuracy of these displacement fields by using the endpoint error, EPE, from optical flow. So in this table, we compare the average EPE between our network and the MBS optical flow. So in general, our network can perform better in displacement fields with strong and significant divergence and curl, while remaining on par in other displacement fields. So finally, what would be the result if we applied our network trained by these synthetic data sets and then directly applied to a measured volume pair? So in this figure, so we show the DVC results for measurement datasets at the bottom row. However, we can only do a qualitative comparisons to MBS optical flow, as it is really difficult to obtain the ground truth dense displacement field in the realistic deformation scenarios. And in general, the proposed Vol-Graph network can estimate the structures of the displacement fields correctly. And in fact, the generalizations of this network is better than our initial expectations, as we did not do any fine-tuning to the trained network, but we only did inference. And in general, our networks can roughly estimate the displacement field, even for the discontinuous and sharp structures in the fracture shown in the magnified regions, so these regions. And this discontinuity should introduce an unknown pattern of structures, while the network can still handle these situations, although we can still observe some patching artifacts in the middle of it. So in conclusions, our work provides an insight into the applications of state-of-the-art computer vision approaches to address classical challenges in material science research. By improving its inference and the patching approaches, it can be potentially applied to other experimental data. And we are looking for collaborations on different DVC problems. And the source code and the trained network are available on GitHub. Thank you for your attention. And do you have any questions?
We have time for questions, for 1 to 2 questions. So that means how computationally expensive your training is?
We trained the network using a V100 NVIDIA V100 graphic cards for 7 days.
On
So-
what kind of GPU?
Sorry?
What kind of GPUs? Like, was it just one GPU or you had multiple nodes?
One. So we can actually extend to more than one of it, but we were more like having a benchmark of the performance. So we trained on one 32 gigabyte GPU memories graphic cards, which is V100, and then it trained for 7 days. Yeah.
Thank you. So our next presenter is Bashir Kazimi. Kazimi, I'm sorry, I mispronounced him.
Oh, thanks. Why it's showing presenter view. There we go. Wrong screen. Sorry, it's sharing the wrong thing on Zoom. Usually, let me just stop share. You share. Well, usually applications. Let's see. Whoops. I was working before. I'm going to share my screen. And then now.
Yes.
Now it works. Okay. Great.
All right, thank you very much. Good morning, everyone. I'm Bashir. I work at Forschung Center Mulisch in the Materials Data Science and Informatics Institute. And today I'm going to talk about self-supervised learning with generative adversarial networks for electron microscopy images. So as you might all know, that the challenges in transmission electron microscopy for deep learning is that you have to manually process and analyze, which is expensive and very time consuming. And here is when deep learning can help. If you want to do semantic segmentation, you have some annotated data, and deep learning will help you do automated identification of those structures, such as nanoparticles, for example. It could also help you in denoising, background removal, and resolution enhancement, as you can see in the image in the bottom right. So you have some noisy images, and if you have a corresponding clean images or images with backgrounds removed or enhanced images, you can train deep learning models to do this for you. And but the problem is if you don't have this data, so lack of annotated data is a big problem here. And this is where self-supervised learning comes into play. And here I'm going to talk about self-supervised learning with generative adversarial networks. So here you can leverage large unlabeled data sets. You don't need to have annotated data to use self-supervised learning. Then you train your models with self-supervised learning approaches on this unlabeled data. There could be many different self-supervised learning techniques, but here we talk about generative adversarial networks. And once you do this training on unlabeled data, you could use it to transfer the knowledge to supervised tasks with very limited labeled data sets. And this is the overall approach. So on the top, on the bottom left, you have the generative adversarial network overview, where you have a generator model that takes a noisy input image and tries to predict a clean version of it. And you have a discriminator that tries to distinguish between the fake and real images. And then after the training is done, you discard the discriminator, but use the trained generator in your supervised tasks where you have limited annotated data sets. This could be semantic segmentation, denoising, background removal, or resolution enhancement. So in this research, we used two kinds of networks as the generator module in our generative adversarial network. One is the very famous network called UNet, which I'm sure you all know, and then the high resolution network. The UNet was experimented with different settings, so different number of residual blocks, and also different receptive field sizes, which means the size of the image, which is responsible for making predictions for a specific pixel. So in the experiments, 4 different experiments were run for each set of model settings. So one is training with random weight initialization. So without any self-supervised learning, you just randomly initialize the weights and train models. And then we also ran experiments with fine-tuning the models that were pre-trained on unlabeled data. For unlabeled data, we trained the model with 3 different sizes to see if increasing the number of unlabeled images helps results in the final segmentation or denoising tasks. Here on the left image, we could see results for different settings of units on the semantic segmentation task. And you can see that random weight initialization does not perform as well as those pre-trained, those fine-tuned with the pre-trained weights from the GAN architecture. And the same way on the right, you could see the HRNet trend is the same. So pre-trained models lead to better performance, but also faster convergence. So here, for both of those models, we tried to save the model weights after each 5 epochs, but here we only show the test results. So the test IOU, the test dice scores for the model after 5, 30, and 60 epochs. As you can see in the initial stages, random weight initialization performs really, really bad, but pre-trained models perform good. But as you continue training, which is intuitive, the pre-trained models, so the randomly initialized models kind of catches up with the pre-trained models, but then it depends on how much resources you have or how much time you have. And this is when this is why pre-training helps you reach faster convergence and better performance. The same is true for other supervised tasks. So for denoising, noise and background removal, and super resolution. Here we only show the results for the high resolution net because it performed better than the unit model on supervised tasks. So we did the remaining downstream tasks with a high resolution network. And again, in all of those 3 tasks, we could see that pre-trained models lead to faster and better, faster convergence and better scores on the validation data. And the same experiments were done for these tasks on the test data. So we saved the model weights and evaluated the model on the test data after each 5 epochs. And again, here we see the same trend where pre-trained models lead to faster convergence and better scores initially, but as you continue training, the randomly initialized models catch up. So the conclusion is that we can learn representations from unlabeled data sets without manual annotation. This could be done with self-supervised learning, but we chose generative adversarial networks here. Pre-training on unlabeled data and fine-tuning on labeled data improves model performance and also speeds up convergence. So these learned parameters can be transferred to all kinds of downstream tasks. In this study, we showed experiments on segmentation, denoising, super resolution, but it could be applied to classification or other downstream tasks that you can think of. So as I said, we use generative adversarial networks as the method of choice for self-supervised pre-training, but there are other techniques. So like masked image modeling. It was also mentioned previously, like the masked autoencoders could be used, or some other contrastive learning approaches like SimClare or MoCo. Different versions of it can be used for pre-training on unlabeled data. Thank you very much. I would be happy to answer questions.
We are going to open up your presentation. Okay. Oh, forgot about that part. Great.
Hello, my name is Kai Nichols. I'm part of the Seagate research group in Seagate technology, looking at machine learning applications. I should stand next to the mic. Machine learning applications to advanced data storage. And this presentation is going to focus on some of our efforts on grain characterization sort of across different applications within the company. So to give a bit of background, Seagate recently productized a technology called heat-assisted magnetic recording, or HAMR. So magnetic recording suffers from a trilemma. So to store more data, you need small grains. But for small grains to stay written with data, they need a very high coercivity. But to write a very high coercivity to very small grains is basically infeasible at a certain point. So to solve this, HAMR takes advantage of the heat-dependent nature of coercivity. So by heating the grains past their Curie temperature, you can write them with a much smaller magnetic field, and it'll stay written once they cool down. The challenge then becomes delivering this heat at this small of a scale, at this nanoscale, requires really sophisticated control of the properties of a lot of different materials. So sort of building on that, computer vision sort of can potentially enable a lot of opportunities for better understanding of the process, structure, property relationship of these materials. We do, for a lot of parts, SEM processing during the production line, and there's a lot of offline experiments as well. But these processes can have hundreds of steps, if not more. And so sort of cursive dimensionality, you need a lot of data about the structure to have any chance of correlating back to process. So within that, challenges that we face to do this kind of computer vision. So the first is just a more typical challenge. Because we're doing SEM, we don't have the best boundary contrast. There are some, grain boundaries that aren't really going to be detectable in the image, so you have to infer where they are. And this is going to rule out more traditional image processing rule-based methods. The second is that there are a lot of application areas and a limited number of resources to work on this. And so finding a solution that can be adapted across these different areas is also important. And then the final challenge, and probably the hardest one, is that because this is a product development environment, things are changing very quickly. And so just doing sort of labeling some images, building a model, it's going to be out of domain next week. And so given these three challenges, we wanted to evaluate whether segment anything can sort of work well for applications, sort of address all these challenges together. So to start with, we wanted to sort of understand the model better. Being a promptable model, an ambiguity-aware model, that opens up a lot of challenges, but also a lot of opportunities. So looking at this small data set, this is a little under 800 grains. They're all actually from the exact same film, all these images. we started sort of understanding, how well does this work? What are we going to need to work around? So as far as extracting some of these properties that we really care about, I mean, within this image, you can capture the general pattern, the means. A lot of these tails you're not getting at all. And in some cases, the tails are going to be the important part. So depending on application, if you're expecting process changes that are going to cause big shifts in sort of the average values of these properties, maybe this is already good enough. If you're looking for more subtle tail behaviors that affect failure mechanisms, maybe this isn't good enough. So digging a little deeper, qualitatively, what we found is sort of 4 main problems. There's 4 main challenges for the model. So the first is sort of small grains are very hard. This makes sense. It's a promptable model. It's not going to find your grain if you don't put a prompt where the grain is. The second is that there's this sort of asymmetric detection of low contrast edges. And this makes sense for SAM. With the way it was trained, asymmetric detection is a good thing. You want to detect a truck, but maybe also the person that's driving the truck, but you would never detect the truck minus the person. But in our case, this is sort of a negative property. And then you have your more expected problems, sort of low contrast edges that aren't detected, and intergrain texture that's sort of recognized incorrectly as an edge. So the next thing we did was sort of break this apart. What is sort of the processing around the model itself, and what is, segment anything alone capable of. So if we look here on the bottom left, this was sort of our attempt to quantify this. So the orange is that like 3 to 10% that the model detects the grain, but then it gets processed out in post-processing steps. The red and the lighter blue sort of show, if we had given it a better prompt, it would have found a good representation for this grain, but the pre-processing steps didn't give a good enough prompt. So now we sort of start to ask ourselves, okay, what can we do to make this better? We know that there's some room for improvement just in the sort of pre and post processing. We have some idea of how much improvement we might be able to get out of that. Sort of move on to how can we sort of being efficient with our resources move on. So the first thing that we really looked at was sort of not the fancy way to improve it, but maybe the practical way in many cases, which is sort of adjusting these pre and post processing steps, the filtering, the image pre-processing, and really thinking about what structures are sort of and what characteristics are inherent that we can leverage. This is great because sort of for end users, it's much more intuitive. Turn knobs, see how it looks. It's much more trustworthy when we're basing it off of things that we know are going to hold over time. But again, that's obviously limited in its power. So the second thing that we're looking at is training on synthetic data. So there's sort of 2 schemes I've mentioned here. One is sort of trying to generate realistic images that you can fine tune on. Methods like style transfer can be very useful in this sort of paradigm. The second is less focused on realism and more focused on concepts, things that we know that the model struggles with. So this idea of like asymmetric boundaries, maybe we can, not on in-domain image at all, but maybe we can train it out of that property. Maybe we can add some like obscuring contamination that we might see in like some of our microscope images and get it to ignore that. And then the final sort of proposal, well, let me add quickly on the last one. So that's, we have some internal project looking at this on how, we might be able to build like a no-code, low-code tool for generating synthetic data so that this is something that's more accessible across the company. And then the final sort of solution is train on human level labels. Do whatever you can to minimize the need for labels, whether that's drift detection, active learning, machine-assisted labeling, using SAM as either starting point for an encoder, as a weak supervisor for another model. Just get whatever you can out of it to minimize the labeling. Do I have time for one more slide, or I can stop there? Okay. So this is some of our learnings on, what knobs are good to turn to improve results. Doing this sort of iterative prompting is much better than just a grid when you know that your objects are going to fill your whole image and not overlap. You can think about basic metrics, grains are never going to be very jagged. If you're getting something like that, you can filter it out, at least in this case. The area, we know that it's going to follow a sort of long tail distribution. We can estimate sort of the bounds on that, maybe from like a few starting grains, and filter things out. And we can do more sort of complex thing. There's sort of mixed results that we've had with sort of, trying to incorporate some like noisy label, like from a more traditional like image filter, or trying to create more complex metrics like, again, going back to the noisy label, how well SAM is aligning with that. I think those still have potential, but they're not as easily and more, they don't have success as much of the time. So as far as giving knobs for the end users to turn, maybe not the best ones. So thank you for your time.
Have time for one quick question.
I'm wondering if you have considered correlating images directly with properties without segmentation or grain size extraction.
I haven't. It's not many of these cases, especially if we're looking at like failure modes, it's hard because it's like a very low labeled data. So extracting sort of the things we have a prior knowledge before into like a lower feature space that are going to affect those failure mechanisms. That's sort of the part of the reason, but that's not to say that it, maybe shouldn't be explored more.
Yeah, thank you.
Thank you. And yeah, come talk to me at the poster.
Our next presenter is Shayla Whitman on application of vision transformers.
Thank you. My name is Sheila Whitman. I'm an applied mathematics PhD student at the University of Arizona. And today I'm talking about how you can use features generated from transformer models for material property predictions. So as we all know, understanding the microstructure property relationships is essential to the materials design process. And recently, machine learning has been used to accelerate this process. But before we can use machine learning, we need a way to quantitatively describe what's being shown in our microstructure images. So there are two main approaches that are very successful. The first is a statistical-based approach. For example, you can use two-point correlation functions to describe what's being shown in your microstructure image to generate our feature vector or quantitative descriptor. However, it is most straightforward to calculate our two-point correlation functions utilizing a segmentation map or a binary image of your microstructure image. So typically, it would be done as you take your experimental image, you perform segmentation to have a binary representation of your experimental image. You calculate your two-point correlation maps and use that as your feature vector. At that point, you can put it into the machine learning pipeline of first performing dimensionality reduction, such as principal component analysis, and then using your machine learning algorithm for property prediction. Alternatively, you can take a data-driven approach, as was previously discussed in many of the talks. You can utilize a convolutional neural network where you can train it from scratch on a large data set of microstructures in order to perform property prediction. Now, with both cases, they are extremely successful at material property prediction. However, with the drawbacks of potentially having to create segmentation maps or having a significantly large data set or possibly fine-tuning if you already have the trained data convolutional neural network, we wanted to see if we could follow along one of the major trends in NLP and computer vision and look at how we can use foundational models instead to extract features for material property prediction. So in this case, we're utilizing DynoV2, which is a foundational model that was released in February of this year. It's had state-of-the-art performance on a number of computer vision tasks, including image segmentation, object detection, and depth estimation. We're utilizing DynoV2 to extract features specifically for material property prediction, but the features that it generates are task agnostic, so you can utilize them for a number of different tasks, such as image segmentation. Now, DynoV2 has a number of models that we tested in this case, and they differ in terms of the number of features that they use, as well as how they were trained. So there's a small, base, large, and giant model, and they have a different number of features, and some were trained via knowledge distillation, while others were trained from scratch. So how this fits into our methodology, what we're doing is we're taking our microstructure images and passing them each individually through DynoV2 to create a feature vector. At that point, we're performing dimensionality reduction in order to avoid overfitting. At that point, we're taking our reduced feature vector and using machine learning for property prediction. We're utilizing two different machine learning algorithms that I'll discuss in the following two case studies. Our first case study was on a digital data set of microstructures. The data set was taken from a previous paper, and it consists of 5,900 microstructures and their corresponding Young's modulus values. The data set consists of 3D microstructures, but in general, these are very expensive to use in industry applications. So what we wanted to do was, instead of working directly with training a model on 3D microstructures, we're training via 2D sections of it. So we're taking our 3D microstructure and we're slicing along the X, Y, and Z axes. So we have 3 individual sections for a single 3D microstructure. At that point, we're passing each section through DynoV2 to obtain a feature vector. At this point, we have 3 feature vectors that are representative of a single microstructure. So we're performing aggregation. We tested 2 different forms, concatenation and mean pooling, to generate a single feature set of features for our 3D microstructure. At this point, we're going to do the same type of methodology as I previously discussed, pass that feature vector through dimensionality reduction, taking our reduced feature vector, pass it through machine learning for property prediction. For our first case study, we did second-order polynomial regression, and we did a grid search through the number of principal components for the best for each of the models. So as our results show, the base model of DynoV2 has almost identical accuracy in terms of in comparison to the 2-point correlation functions as our baseline. We tested the small, base, large, and giant models of DynoV2, as well as testing if we interpolated each of the images to 224 by 224 for the base model. While these results were extremely exciting, we predicted that working with the experimental images instead would show even better results because we would reduce the need for creating segmentation maps. So again, looking at our digital data sets, they're already binary images. So again, it's very straightforward to calculate the 2-point correlation maps. But in the case of experimental data, there's that additional step that you have to do. So your 2-point correlation maps, they're most successful if the segmentation is performed extremely well. But in some cases, segmentation isn't as robust, and it can be more difficult to come up with the segmentation maps. So you're excited to see how DynoV2 would perform directly on the experimental images. So our second case study was looking at 103 experimental microstructures extracted from about 20 different papers and their corresponding Vickers hardness values. As you can see, the microstructures differ pretty significantly in shapes and geometries, but they're all super-base nickel alloys. So again, what we did was we took each of our experimental images, we passed it through the pipeline of DynoV2, getting the features, dimensionality reduction, and then machine learning. In this case, we did linear support vector regression to compare against the previously published results of the 2-point correlation function maps. We also compared against extracting features from a convolutional neural network. And here are our results. Again, we tested all 4 of the DynoV2 models, as well as a convolutional network and the 2-point correlation function. Again, we have almost identical results, but this was without the need for creating segmentation maps. So we directly inputted our experimental images into DynoV2 to extract features and got only a 1% difference in error compared to 2-point correlation functions, which were our baseline, which needed the segmentation maps to be produced first. So in summary, we say that utilizing foundational models could be a good alternative to working with either 2-point correlation maps or convolutional neural networks as a feature extractor before utilizing it for different tasks, including property prediction. But again, you can also use that same feature vector for other tasks as well, such as image segmentation. And that's all I have. So if you have any questions, I'd be happy to take them now or come visit at the poster session.
I'm just wondering if you could maybe just go back to the previous slide.
Yeah.
Could you just very quickly flesh out the very last step that you said you did PCA, got a reduced feature, then you had some sort of ML. What did you use in that last stage there?
Yeah, so it differed based on the 2 case studies. The first case study, we utilized polynomial regression, and the second case study was linear support vector regression.
And I have a quick question about, did you try other dimensionality reduction techniques instead of PCA, like, for example, UMAP?
No, we did not. We just stuck with PCA.
Okay, thank you. And right now we are going to see posters, and we'll be back in this room at 11. And there'll be 2 invited talks and panel discussion.
Posters are upstairs.
Right.
Yeah, posters are upstairs in 4E. Fourth something, 4th floor. For the Zoom people, we will be back at 11 a.m.
Pacific time.
Pacific time. Oh, wow. Figured out how to get it to not show presenter.
What? Sweet. Thank you so much.
Yeah, well, I need it because this is how we're gonna get to not crash.
Oh, nice, nice. Oh, now you can like copy the screen with sharing on Zoom. Okay, cool.
Give like little bit more time.
Yeah, sounds good. Yeah.
It's tricky to get through.
It is. I accidentally went out a different door and ended up on the other side of the building as I was coming down. I was like, wait a minute, where is it? Luckily, the signs were very helpful.
Yeah.
And I like power walked over here, so I'm glad to have a second to.
Yeah, even,
Yeah, it was also funny, like poster session. You keep walking, then another poster session.
Yeah.
You start wondering when it ends.
Yeah,
Somewhere.
it's a lot of posters. Yeah. Yeah, I can't believe they like shift through them like every 2 hours or so too.
yeah, they have multiple, like not even, yesterday they did, I think 2 days they're just morning and afternoon, but
Yeah.
like yesterday they had like 3 or 4 like time blocks that you could get assigned
Wow.
to.
Was strange, so there are two poster sessions, morning and afternoon, so I expected, okay, you would show up at 8 AM, let's say, put your poster, and then at lunchtime or before lunch break, you take it up. No, the email I received from the conference organizer says that only during the designated time slot you can put it on, and I don't know why.
Yeah.
Like during our break, and it looks like nobody else, at least during the morning session, was going to use the same poster box.
Oh, really?
Yeah.
Yeah, it's a shame they don't let you keep it up. Yeah, if nobody else is using support.
Yeah. Especially since everyone keeps going back to the poster room because that's where all the coffee breaks are.
Oh, is it?
Yeah.
Yeah.
So I'll have to check that out after. Yeah, I was wondering, I was like, oh, where's the coffee?
Yeah, yeah, I figured that out yesterday because everyone was just, we're all on coffee break, and it's like, where?
Oh, nice. Yeah, maybe I should have went for that first. I went to the posters first, and then I'm chatting, and then I was like, oh, wait, it's time to go back already.
Yeah.
How long is this poster session? I feel like it goes a little longer, right?
So basically it's up to us. So
Yeah.
in our case, it's until 11.
Oh, okay.
So 5 minutes, let's give 5 minutes to come.
Oh, yeah, sure, yeah. Yeah, I think it went by faster than expected, so.
Yeah, I don't think I guess at other workshops I've been to in like machine learning, usually the poster session's in the rooms. Like
Yeah,
people just
yeah,
like put
that's-
up posters in here, so that's what I was expecting.
Yeah, that's
That's kind of nice.
that's what
yeah,
I
it's like
expected
that.
as well. Because like I went to ICCV last year, and that's exactly how it was organized. The same room.
Yeah. Do you have a machine learning background?
I started doing it for my postdoc.
Yeah.
So my background's in like sort of similar, my background's in situ TM.
Oh, cool.
And then you also get just like lots and lots of data.
Yeah.
And so it became really obvious near the end, like we need methods to process all of this
Yeah.
data. So
Oh, that's
I decided
awesome.
to do it for my postdoc.
Cool. What kind of in situ tests were you doing?
I was doing like a lot of environmental TM,
Yeah, okay.
environmental TM, and actually optically coupled TM. So
Oh,
basically
yeah.
sending light in and actually seeing how things react under
That's
illumination.
sweet.
Yeah.
Cool.
So a lot of like catalysts for the catalysts.
Yeah.
that type of
Oh,
research.
yeah. I guess you would need something like that to do photocatalysts. That's super interesting. Cool.
Yeah, so a lot of nanoparticle analysis.
Oh, yeah.
It's basically all nanoparticle analysis
Yeah.
and particle morphology and yeah.
If you have a TM, you might as well be doing nanoparticles. Yeah.
Yeah, that's true. Sample prep is so much easier.
Oh, yeah. Oh, yeah.
Yeah, I guess we're reasonable.
Let's wait.
Okay.
Till 10, and instead of ending at 12:50, you'll end up at 1.
Okay. Oh, yeah, that works.
Yeah.
Nobody's gonna be like, oh, I had my reservation at 12:50.
Yeah.
And the lunch goes until 2.
Yes.
Yeah, so there'll be time to grab sandwich.
Okay, nice.
Yeah, Berkeley, actually, everything unofficially starts 10 minutes past whatever time you set to be the start time. We call it Berkeley time. So
Oh,
if you
really?
say something starts at 1 p.m., everyone expects like it's not going to start till 1:10 p.m.
Oh, nice. That's interesting.
Yeah, but then up at the National Lab, it's not that. You don't
Oh, yeah.
It's always interesting when you have both like UC Berkeley and Berkeley National Lab.
Yeah.
Everyone has a different metric of when is the start time.
How tightly is the university and lab joined?
I would say like the UC Berkeley Material Science Department is very tight with the Berkeley National
Oh, yeah.
Lab. Yeah, and then yeah, it's very good. I mean, because it's literally a bus, like a really quick bus ride,
Yeah.
shuttle ride.
Okay.
It's like UC Berkeley down here, and then the lab is basically up the hill, and
Oh,
like up the
okay.
hill, and then the lab entrance is right next to
Oh,
UC
yeah.
Berkeley.
Oh, nice.
So there's a lot of cooperation. I
Okay.
think people go to each other's seminars.
Oh, cool. Are the students allowed to use some of the characterization equipment at Berkeley Lab?
Yeah, so I'm at the Foundry, Molecular Foundry, and then
Yeah.
I would say a good number of our users are UC Berkeley students and faculty.
Oh, that's cool.
Because it's like very easy for them.
We'll start at 11:10, just giving time for people to come back.
Let's see.
Please no, the last speaker.
Oh, he came back.
Oh, okay.
Yeah. He went to go get coffee.
Okay.
Oh, nice.
Yeah. And I made sure that his thing works.
Okay.
Yes.
Yeah, his abstract looked very interesting. I'm excited to see that. Yeah.
Okay. I don't know whether they named it or not, but initially it sounded very cool. It's segment anything, everywhere. It's something like that.
Yeah, I wonder if it's named after that movie.
Oh, yeah.
Everything Everywhere All at Once, whatever, yeah. You like to do well in machine learning and the deep learning field, you have to have clever names for your papers. What was that? An image is worth 16 by 16 words. And
Yeah, that was
attention is all you need.
paper, yeah. 3 or 4 years ago, probably. Introduced vision transformers.
Yeah.
I don't know that.
Definitely nice to have clever names. I wish we could have more fun. I tried to have fun with some of my papers in grad school. My professor was like, we gotta make it boring and scientific.
When attention was introduced, the paper was called something like attention is all you need, but 2 or 3 years later, there was another publication. Attention is not
Oh, really?
everything that you need. Something like that.
So I think that's a much better word for what
Yeah,
that is.
Yeah, let's.
Yeah. A lot of crazy things.
So welcome back to the second half of our workshop, and we'll have 2 invited speakers, followed up by panel discussion. So let me introduce our next speaker, Joshua Stackner. He's a materials informatics scientist at NASA Glenn Research Center. His research interests and expertise include applying computer vision and deep learning to materials design and discovery, automatic microscopy analysis, transmission electron microscopy, institute chem, and surrogate modeling. Joshua has been working on the team that has recently released pre-trained micronet models for deep learning-based microscopy segmentation and analysis with the less training data. There were over 10,000 downloads of these models over the last 2 years.
Welcome, Joshua.
Thank you very much, Alexi, and yeah, thanks a lot for organizing this workshop. So this work was done in collaboration with many different folks. Most of the work was done at NASA. Some aspects of the project were done with a Belgian steel research company called AUKUS. So this work is funded from Congress to NASA to the Aeronautics Research Mission Directorate. And we call aeronautics the little a of NASA because we only get about 3% of the budget. But they say for every dollar invested in NASA, we give $7 to $14 back to the American economy. And I really think that aeronautics is a large outsized proportion of that. So when we're making materials, we start with the processing and go to the properties of the material. But we'd really like to invert that and do inverse design where we have the properties that we need for the next battery that's going to change the world, or the next wind turbine or computer chip. And we want to find the processing that's going to get us there. And we can do that with inverse design techniques. One of the common ones are Bayesian optimization or active learning, but there's a lot of other ones as well, where basically you need some data, a machine learning model that links the properties to the processing, do an optimization, and then you can predict the recipe that's going to get you the optimal properties that you need. But we're missing something with this, as I'm sure most of you in this room are aware, and that's the microstructure. Because very small changes in the processing space can have sudden discontinuous changes in the structure space, which has sudden discontinuous changes in the property space. So here's just like a basic phase diagram where if this is like steel, for example, then even like 0.1% differences in carbon can have a huge impact on the microstructure, which has a huge impact on the properties. And that's just one thing, that's just composition. If we hold it at different temperatures for different amounts of times, cool it at different rates, that's going to have huge impacts on the microstructure, which in turn impacts the properties. So it's really difficult to get a model that links processing of properties to do that directly without featurizing the microstructure space because of those sudden discontinuous changes and the requirement to like sample at each individual step there. So we really need to quantify the structure because the properties are a function of both. But how do we quantify the microstructure? It's not a trivial problem. So the old way of doing it was with manual quantification using ASTM standards. They would do like put little grids on the paper, draw little circles using the intercept method, or use software aided. But it's very tedious, time consuming, a lot of potential for bias, where one researcher might say, oh, this ligament is to the orange line. Somebody else might say it's to the yellow line. And then you just can't measure that many things, do that many different experiments, test different features that you're trying to change. So automatic quantification, I mean, everybody at this conference is doing automatic quantification. That's what we're here for. So there's a bunch of different ways to do that. There's like statistical methods, 2-point correlation type that Sheila was talking about. And there's recipe-based where you like build a bespoke computer vision algorithm that will do something. For example, you could do denoising, do Otsu's method for segmentation, and then do like a distance transform and skeletonization, multiply them together, get a radius map, and then boom, you have a radius measurement along every single diameter along here. But that's kind of painful too, because you have to design a bespoke algorithm for every different material. Also, it's not robust to large changes in the sample space. And then another approach is data-driven, where you can just use a machine learning model to get the latent features directly. So I'm going to be talking about what the pre-trained encoders that we have developed will improve the segmentation step, which is the first and hardest step often of the bespoke algorithms, and then it also improves the data-driven step as well. So here is a convolutional neural network. It's the current state of the art for image analysis to some extent. Vision transformers are coming on in a big way, but most of the best vision transformers have convolutional layers in them still. In any case, whether it's a vision transformer or convolutional neural network, this technique still applies, where you have a pre-trained encoder which represents the image, and takes this image as an input and represents it as a feature vector, and then it has some task-specific head. And so what is done is you train it on millions of pictures of everyday life. It learns filters along the way to predict the class, And then you can take the task-specific part off through transfer learning, embed it into a different type of model, like a segmentation model, instance, segmentation regression model, semantic segmentation, whatever you want. And it's already learned a lot about computer vision here. It learns a lot about these filters. So you need much less of this segmentation data, which is much, much more expensive and less available. So you can train a lot better. But what are these filters learning? In the first few layers, they're learning things like corners, edges, textures, maybe in the next few layers. But then deeper in, if you look at, there's some papers that explore what these models are looking at deep in the deeper layers of the neural networks. There's a lot of dog ear detectors. There's a lot of like cat detectors in the model deeper on. So those aren't going to transfer as well to microscopy data. And so what we did was pre-train on 100,000 images of microscopy images, and we trained it to say, hey, this is material 1, this is material 2, so that it got a better feature representation when applied to downstream in-domain tasks. And I'll talk about, for this presentation, the pros and cons, where we've seen this working, where it hasn't been working as well, and then talk a little bit about, more recent, like we're getting all these foundation models, which are trained on tons and tons of data. And so it's kind of hard to keep up with that, even though it's not in domain. And there's like a trade-off between, are we doing in domain or more bespoke models? It's definitely an interesting area of research that's moving quickly. So our classification models, so this is the pre-trained encoder that we trained. We did it in classification. We had 54 classes, polymers, composites, metals, SEM, TEM, all sorts of microscopy images, whatever we could get our hands on. Since they were so much larger, it ended up being about 400,000 equivalent of ImageNet images. We used the augmentation that was used in to train the EfficientNet set of models, very standard. We used early stopping, learning rate decay, and we trained all of these encoders. And all of these pre-trained encoders are now available online at this website. And so you can use them wherever you would use an ImageNet model. You can just slot this right in. We have a sample code of how you can slot it in with just like a line or two of code. So I'll be talking about how sometimes it works great, sometimes it doesn't work quite as well. But the nice thing is you can try both in a change of a line of code. So you can easily add it to your like hyperparameter optimization framework and see if it works. So looking at the top one accuracy of all of these different models. So some of the models were pre-trained on just the 100,000 microscopy images from scratch. And then other ones were taking the pre-trained ImageNet encoders and then fine-tuning them on microscopy net, and we get this top one accuracy. If you use these pre-trained encoders, we found that using the ones pre-trained on ImageNet and then MicroNet ended up working the best, and they'll all be there. But we don't really care how well they do in classification. You never like pick something up off the ground and like throw it in your $1 million microscope and you're like, oh, I wonder what this is. Let's try and classify. What we really care about is like the other tasks that are more complicated, like segmentation. So we did several experiments, and I'm going to talk about this one experiment in analyzing how it does in segmenting the nickel-based superalloy. And we trained all these different encoders, including UNet, UNet++, DeepLab V3. The nice thing about these encoders is that you can just like slot them into any sort of different model very easily. We used intersection of reunion as the quality metric. Okay, so here are the results on the nickel-based superalloy experiment with ImageNet and MicroNet. Here, top row is ImageNet. Here's our training data. We had somewhere between like 10 down to 1 images, and here's the test data. So this one corresponds to this, and this one corresponds to here and here. You want to see black and white. You don't want to see the false positive or false negative. So with 10 images, both models end up working really, really well. You can annotate 10 images and then get good results for this data. But when you drop down to just annotating 4 images, the ImageNet models really start to drop off, while the MicroNet model still maintains pretty near high accuracy. With only one image, this one image here, the ImageNet model has lost a lot of accuracy. It's lost all the tertiary precipitates here and combined all the secondary precipitates in this nickel-based superalloy. So if you were to try and do size analysis on this, you would really struggle here, whereas this one does much better. So with this, on this data set, you have to annotate much less data in order to get good segmentation results. On the environmental barrier coding data set, which you can look at the paper and see, this one was not quite as good. It was still better for micronet, but not as starkly great as this one. We also looked at allodomain data. So we have our training data, and then our test set comes from either completely different alloys or different microscopes or training day for the intern. And we wanted to look at how well these models perform to these auto distribution data, because man, that's been a huge problem for me when I was before like CNNs, and I was making bespoke segmentation where the microscopists would come back and say, hey, here's another set of micrographs. I took them exactly the same way, but man, they look completely different and everything just falls apart. So I wanted to explore how well it works. And so as you can see, although like the accuracy is like 78.5% versus 72, if you look, it's a lot better at maintaining the getting the secondary precipitates, maintaining the separation in here. And at the end of the day, if I have to relabel one or two because it's so different, I have to relabel like a lot less. I just have to annotate one more image, and it usually works much better. So here's doing some size analysis measurements on the segmentation images, and we can see that the micronet models are much more accurate compared to the ground truth at getting the size features of this material. So we've applied this to a ton of different materials. So these nickel-based superalloys, this is a new alloy GRX810, which we just developed at NASA, that has like several orders of magnitude more creep strength than other alloys. And so we can throw that in jet engines, turn the jet hotter, and then we're running at more efficiency. And just this, if you increase the temperature by even like 10 degrees C, you end up saving like billions of dollars a year in fuel costs, which is a lot of carbon emissions that you're saving as well. So we're at NASA working really hard to increase the efficiency of jet engines. And one of the ways is by making these materials. And so what we're doing is linking how we're making the material to the structure of the material, to the properties, so that we can find what levers we can tune to get more efficiency out of our jet engines. So this is another example of an environmental barrier coating. So this we put on top of the metals in the jet engine, and it keeps the environment out. It keeps them cooler, and especially keeps them from oxidizing and like having all sorts of corrosion effects. And so the problem with this material is this oxide layer here, it starts growing and it has a different coefficient of thermal expansion. So as it's being, you turn the engine on and off, you like fly your jet, land your jet, sit it outside, it's growing this oxide and cyclically loaded at different rates and causing cracks. And it lowers the lifetime of the engine, basically. So we want to understand the growth kinetics of this oxide and see if there are ways that we can change or reduce the growth of that oxide. So we hooked it up to our segmentation model, and these are quite different images. So this is an example where they come back and like, hey, now I have this one, and I did have to relabel this one. But I just have to relabel one, and then I can do the image analysis. I segment it, I get the cracks, then I can easily get the thickness of the oxide layer, get the crack spacing, and then get the roughness. I don't know if it's fairly clear there. It just automatically gets the roughness of that. And we were thinking that if we could find a way to control the roughness, then maybe we can control the growth kinetics. Maybe we're pinning different parts of the oxide layer from growing. And we're exploring that currently. We developed a software that just makes it super easy for the end users to analyze their images, and you can just like throw 1,000 images in and it can do it over lunch. And this ended up being about 180 times speed up over manual analysis, because they would have to do one sample, heat it for like 10 hours, take an image of it, heat it for like another 1,000 hours, take an image of it, and then do like hundreds of measurements along the whole thing, do that for several different architectures, and it ended up being like just thousands and thousands of images that you have to look at. So it was way too painful to do that manually. So this was a huge help to be able to do that automatically, and really helps us. It pushes the rate limiting step to not be the microscopy analysis, but like actually taking the micrographs and doing the experiments. So we've applied it to these two alloys, Inconel 718. This is a additively manufactured copper alloy that we developed at NASA. And this one is actually a full 3D printed build, and we have a RoboMat that just like takes a whole bunch of images across the whole 3D printed cube, and then slices a piece off, and then like takes a whole bunch more images. And so it's just like a terabyte of data for like one little thing, and like it would just be impossible to hand measure that. So it's great to be able to automatically segment that and then get all the features out of it. And then with the automatic analysis, we can also have a much more confidence in the distribution of the measurements, which is important because failure often happens at the extreme values of the statistics. So there are other ways that we can use these encoders to quantify micrographs. So I was talking about doing segmentation, all of these so far. Segmentation, build a bespoke computer vision algorithm to extract the features that the scientists said that they care about, like the thickness, the aspect of the oxide, maybe the size and aspect ratio of the precipitates. But we can also just do direct analysis of the feature vector that's in the neural network here. And then we could either do direct regression, we can extract that feature vector, do principal component analysis, and then hook it up with other models that link processing to properties and maybe do active learning or Bayesian optimization. So one thing we wanted to compare is what's better, like can a computer vision engineer design a image analysis workflow and get the features that the scientists say they want? And does that end up being better than just directly taking the latent feature vector? We figured that if we had a lot of data, the latent feature vector would probably win because it might identify things that the researcher doesn't know what to look for in the micrograph. But we figured that you could probably just engineer something that would work better in lower data. But honestly, I'm tired of making like these computer vision algorithms. I'd rather just extract that feature vector, move on to the next project, the next project, the next project, without having to spend weeks developing for each individual one. So this was in collaboration with AUKUS, where we did physical feature extraction, where we built a computer vision algorithm or the segmentation. So this is MicroNet segmenting the carbides, austenite boundary, and this boundary class, which is kind of a general martensitic boundaries and other boundaries as well. And then we did the physical feature extraction. We looked at the phase area fraction, the region area, boundary length, aspect ratio, carbide cluster density. And then we did PCA down to 15 features just to keep it at the same dimensionality as the latent feature. So we're comparing apples to apples. And then the latent feature extraction, we ran it through the pre-trained encoder, got the feature vector. I think it was either 1024 or 2048 length, depending on which encoder we used, and then did PCA to 15 features. Then, so the first thing we did was we did classification accuracy. So we had 18 different steel alloys that were processed in different ways. They wouldn't even tell me what the alloys are. They were very secretive about it. But for the latent features, we ended up getting an F1 score of 0.86. But for the physical features, we got 0.75, and you can see some confusion in this area here. A lot of the classes it did really, really well with. All of these had about similar carbon in the alloy, but were just processed in different ways. But the pure latent features ended up working better, so that was kind of nice. So when looking at the classification accuracy of ImageNet compared to ImageNet and MicroNet versus the features, in this case, the MicroNet pre-training ended up working a little bit better than the ImageNet pre-training, except for the VGG16 model with batch normalization, but the other ones ended up working better with MicroNet. Now, here's some of the clustering maps of using the latent features versus the physical features. And as you can see, this is just U map down to 2 dimensions, but you can kind of see that the latent features end up grouping them better in these little clusters for like, obviously makes it easier for classification. We also looked at regression accuracy and of the latent features versus the physical features. And in this case, we're predicting the hardness of the material. And in this case, the ImageNet ended up working a little bit better in most of the cases, except for the ResNext 50 encoder, and quite a bit better than the physical features, but still very high R² scores actually for regression. And I guess the data set size was, we had about, for all 18, we had between 3 and 8 images, so maybe 125 or so images total in our training data. But we also did extrapolation, because you often in material science, like, I mean, machine learning models are great for interpolation, but we really want to find the next best material. We're not looking for the average material. We're looking for a new battery that's going to be better than all the other ones, or a new, stronger, lighter or metal alloy. And so in regression, for Gaussian process regression models that took the latent features and then predicted the hardness, the ImageNet models actually did quite a bit better than the MicroNet models. Now, we also looked at an ordinary least squares regression model, which very much outperformed the GPR model in extrapolation, which kind of makes sense. Like GPR, Gaussian processes don't work that great in extrapolation compared to linear regression, whereas in interpolation, the GPR did better. And also in extrapolation, there was less of a difference between ImageNet and MicroNet. But it's kind of interesting, the ImageNet model has been trained on millions of pictures of everyday life, whereas the ImageNet model or MicroNet model has only seen like 100,000 images. Yes, they're fairly in domain, at least their materials, they weren't this material, but it's just kind of interesting that maybe it's seen so much more that that's what makes it better at extrapolation, because it's seen so many more things. But I'm honestly not sure. So another thing we did was direct property prediction of these fracture surfaces from the Artemis core stage, which is like the big orange part of the rocket. They're all welded together in these huge metal sheets. And we did property prediction, and then also extracted features and used those to identify a better welding process space, to basically weld them better with less chance of failure. But also one thing that was interesting is we used this we predicted on different patches of the images and did a heat map of where it thinks it's a bad defect and where it thinks it's an okay defect, because we were seeing this defect here, which whenever there was a bad fracture, it almost always had this defect, but that defect didn't always make it bad. So we were kind of using the model to help guide us as what is a bad defect versus what is not necessarily so bad, even though it had looked very similar. Now, that patch-based method is not the best method. I would, in the future, use gradient activation or like activation maps, something like called GradCam or gradient tape, and you can get much better heat maps. But this is what we did at the time. And then, so on this one, ImageNet, MicroNet ended up giving us less errors, even on the full data set. And then as we go to less data, it ended up giving us less error. And then we also, so these encoders, anytime you can use an ImageNet and pre-trained encoder like BGG to ResNet to ResNext or Inception, any of those things, you can easily slot in the MicroNet model, so you can just try it. Even like the newer clip models and stuff like that, they all have these type of encoders like in there somewhere. And so we hooked it into the faster RCNN model, and actually we were quite surprised that this worked at all, because there's a lot more going on in the deeper parts of the model. We took a pre-trained faster RCNN model that was pre-trained on the, I believe, COCO data set, on instant segmentation, and then we just ripped out this part and stuck in our model. And the feature vector is a lot different. So we were expecting, this model would have no idea what the brand new features that it was giving it, but it was able to retrain, I guess, the interface layer here. Ended up working quite well to slot in MicroNet models in there, and we were able to get better instant segmentation on these melt pools. And we did instant segmentation here because, so this is a 3D printed material using laser powder bed fusion, and the processing of the laser as it's going over, it's going to melt a little bit of material, and then it's going to re-solidify. So we have to look at these melt pools, and they're all overlapping, and we want to quantify how different laser parameters like the speed and power affect those melt pool dimensionality, which is going to affect the grain structure and all kinds of things, ultimately the properties. And so by using this, it gives us a feature that can build the models to go from process and structure properties and more quickly optimize our laser processing without requiring as many experiments. So we've used this on all kinds of different materials. It's being integrated into a Climex software who makes an image analysis software for microscopes. ASM International is using it to develop a microscopy analysis toolkit. It's being used by a pipeline company to new federal regulations are requiring that
pipelines that are like, they could be 100 years old. They're carrying like all kinds of nasty chemicals, and they're really expensive to replace. But if they fail, then it's like an environmental disaster, basically. So it's really important to be able to predict when they're going to fail, because you can't go around replacing all of them, but you want to make sure you do replace the ones you do. So new regulations require them to understand how the microstructure relates to whether they need to replace them a lot. So they're exploring using MicroNet for that. Yep, and all this is publicly available with examples on how to interface it with several other types of models. So to conclude, we pre-trained microscopy-aware pre-trained encoders on 100,000 in-domain microscopy data sets. And a lot of times it works better on microscopy data. It doesn't always work better, but it's really easy to test it out. We've used it to automatically extract microstructure features and establish the processing structure, that should be property relationships of different materials as we design new materials. It can be easily applied to any computer vision architecture that uses pre-trained CNNs. I would like, we did test it out on vision transformers, and but it just I think 100,000 images is just not quite enough to fit the large vision transformers like Dino and the other ones. Like, man, they're like ImageNet is like smaller than what they're pre-training them on these days. It's like orders of magnitude smaller than what they're using in natural images. So also we also tried, so this was supervised pre-training. We also did self-supervised pre-training with like SimClear and MoCo, but those didn't quite work as well either. On 100,000 images maybe it was we messed something up, or maybe it wasn't enough images, but it just didn't quite work as well. So that's why I think there's a real need, I think, in the community for a large open source data set of microscopy images. And I guess I'm kind of the like pot calling the kettle black, because I have my 100,000 images and NASA won't let me share them. Unfortunately, I would love to like just give them out. I think I can get like 50,000 of them out, but I'd love to see like different communities, universities. Man, there's gotta be like millions and millions of images around different national labs, every university. We could make a giant data set. So if you're interested in sharing images or working with me to create such a large public data set, please reach out to me. Talk to some folks at NASA. We have a contract with Amazon to host some of this data on a bucket, and it'd be great to have like a large ImageNet for microscopy data, and then we can train the dinos and do self-supervised learning and build the vision transformers, and also explore how maybe microscopy analysis it might need different things, different architectures that's going to make it good compared to natural images. Because just there are a lot of differences that we've been discussing through this conference, like the mini instance issue, but there's also like a multi-scale effect going on where like you might have on one level the grains are making a huge difference, but then on the other level, like twin boundaries or like really small precipitates are making a huge difference. So there's a huge multi-scale effect that different architectures might be really interesting to explore, especially different attention architectures, I think. In any case, end of ramble. Thanks.
Thank you, George. Time for questions.
Fine.
So talking about the need for like a large public microscopy data set, do you think that there's benefit to combining with sort of other domains? So like right now, there's also a computer vision for microscopy workshop for medical vision going on. Or do you think that materials and medical are different enough that it might not be beneficial?
That's a great question. I think it's something we might have to test, and it might be a case-specific thing. But I would guess that, I mean, medical images are much more similar to materials microscopy than natural images. So I think it would actually be useful. And if we're going to be building large foundation models anyway, we might as well have one that's trained on medical images, and then if we want to fine-tune it on materials data. So I think, yeah. Yep.
I wonder, was the confusion
Oh, yeah, sure. The question was on whether uncertainty has been investigated on the segmentation masks, and we didn't investigate uncertainty on them. But I believe there are, yeah, I think some of the other presentations have explored that, like the first one. Yep.
So I'm curious, so when you train on ImageNet versus MicroNet, so SM images are probably like grayscale, right? And the other one is like tricolor. So does ImageNet like have an inherent advantage in that sense?
Well, I converted all my SEM images to be RGB. There are ways to like convert the weights to work with grayscale images. Some of the images were, I mean, that's a good question. But I would think that the grayscale images are more in domain than the ImageNet images. And so if we're applying them to grayscale images, then perhaps pre-training it on a similar number of grayscale images would be the same. But they're only grayscale in appearance to us. They're actually RGB anyway, just to make them compatible with the ImageNet pre-training. Yep.
For the big data set, have you looked into extracting figures from papers?
For the big data set, have we looked into extracting figures from papers? Yes, actually, I did. Yeah, I wrote a script that went out and scraped. I got like 200,000 images from figures, and then made a classification model that does pretty good at separating. I just got all the figures from microscopy journals, and then got just the ones that were microscopy. I got a few random figures in there, but pretty much mostly microscopy. And then I tried to do so that I think would be great for newer models. Like, so I tried to do self-supervised pre-training because I didn't have labels for them. That worked pretty well. But man, now the multimodal models can take such rich information in the training. Like, I would love to see somebody like train on all the figure. Oh, I had the figure captions with them too. So you could do something like Clip, hook up the figure caption to the image, put it in the same space, train a model. I think that would be awesome. When I was testing it, it just was, even 200,000 images, it just wasn't enough data. And it was just, even though it seems like a lot, it was a different order of magnitude compared to what they're doing with natural images. So I think we just need more data and we can do it. Yeah, but great question. Yeah.
Okay, let's delay other questions for poster discussion. Let me introduce our next speaker.
Thank you.
Jianwei Yan. Jianwei is principal researcher in deep learning group at Microsoft Research Redmond. His research interests span in computer vision, multimodality, and machine learning. Currently, Jianwei is focusing on building next generation vision and multimodal foundation models. The team he has been working with is the first few in this line of research and have produced a series of works like UniCL, recently LEAP, K-Light, and the foundation model Florence. Generally, is decoder, XDecoder, and SEAM, a promptable and interactive model for segmenting everything, everywhere, all at once in an image. Welcome.
Yeah, yes, thanks a lot for the introduction and also the invitation to be here. So I'm very honored to be here. And so honestly, I'm new to this domain, but after listening Joshua's talk, I feel this domain is very quite interesting and it's worth a lot of kind of attention and exploration of research. So yeah, today I'm very glad to be here to introduce you how we strive for this kind of prototypal vision foundation in the wide from head to tail. So before that, let me introduce this figure. So I want to draw attention to this figure, the landscape of vision task. So if you look at this figure, you will find, okay, the computer vision, actually there's so many type of problems, right? So there's so many type of modality as input. So it could be the static image, it could be the video sequence, and also it could be associated with the text, audio, and some other type of modalities. And the second part is that, okay, there are different granularity of tasks. So it could be image level, like classification, like image text retrieval, like image captioning. It can be also region level task like object detection, grounding, etc. And of course, pixel level task segmentation, as we had a lot in the last talk. So there could be different type of output as well, right? So it can be spatial, edge, and bounding box and masks. And in the meanwhile, actually, we really want to be also semantic. So we want to predict the associated label or associated description for different regions, for different bounding box, etc. So overall, actually, you will see, okay, in the whole community, actually, people are trying to address in so many type of different problems. So this will have some kind of introduce some kind of challenges to people that are starting. But in the last few years, actually, we have seen great progress to achieve the unified kind of vision foundation to address so many type of different problems. So in the next, I will introduce some of the recent work that lead us to more general purpose kind of vision foundation. So in the first part, I will introduce you, okay, how we can convert a closed set vision model to a multimodal or open vector model, because the intuition is pretty simple, right? Language is a common space to share the visual information. So people usually describe the image from different domains in language and also communicate with each other. And secondly, that, okay, so the zero-shot transfer capability can be significantly enhanced by converting the closed set vision problem to a multimodal vision problem. And the second point is that, okay, how we can convert or unify the specialist model to multimodal unified model. The intuition is that vision tasks are fragmented, as I showed in last slides, and it was a multi-granularity, right? But the benefit of unify is that, okay, we can potentially achieve the mutual benefit across different tasks at different granularity, because most of the information from different domains could be complementary. And finally, if we can unify them together into a single unified model, then this information can be communicated, can be integrated together. And the third part is that we want to jump out of representation learning to the prompt interface. So previously, the old-fashioned computer vision community actually are trying to overdo the representation learning. But representation learning is just one of the steps to achieve the promptable or general purpose vision foundation. We want to make the model itself have a strong kind of promptable capability, so that we really can have the ability for the model to capture user intent and facilitate intimate human AI interactions. So this could be very important as well. So I will walk you through 3 works, each of them fall into each of the domains. And later on, actually, I will exactly introduce what I have done by transferring this kind of general domain, general purpose vision foundation to the domain, to the specific domain, like medical domain. Someone just asked. So let's first go through the first one. Supervised learning, right? So we all know, okay, the MNIST, CF13, and the ImageNet. A lot of people know this, and even a lot of people train a model with this data set. And people have developed different type of architecture, like VGG, as Joshua mentioned, and WhatsApp and the VIT, etc. But the problem is that, so one of these kind of supervised learning actually always, okay, assume that the image category is just maybe a set of labels. But this label actually itself doesn't have any meaning. It's just 1, 2, 3, 2000, something like that. Actually, behind these labels, we have more information. That is the semantic labels. So the semantic space actually is discarded as well when we cope with this kind of supervised learning. But this is not good, and this is not perfect, right? So in this sense, actually, we first want to bridge the vision and the language. So for the first part, actually, we want to bridge the vision and the language in the image level. We propose some kind of unified contrast learning in the image text level space, so that, okay, we really can merge so a large amount of image level data. It could be the image level data. It could be the image text files. And second is that, okay, we can further extend it to the region level, right? So we really want to then the model not only understand the image globally, right? So image consists of multiple components, multiple objects, multiple regions, and we want to make it possible to understand very detailed information in the image, spatially and semantically. So let's first go through the first one, how we bridge the vision and the language. So we propose Unicell, and the idea is very simple. So we build a new space called image text level space. So if you look at this space, so the supervised learning is just, okay, combining the image and label is just one point, as you can see, the blue point in this space, 3D space. And they just want to lane the projection and the mapping between the image and the label. And the contrast learning, like CLIP, like other type of model, actually only trying to lane the element or lane the matching between image and text files. And it's one-on-one matching. But here, actually, we propose a UniCell. We want to achieve the best of both worlds, to merge seamlessly the image label data and the image text file together, so that we can really get not only just discriminatory representation, but also open vocabulary understanding of all of the visual data. And behind this idea, actually, we propose a unified contrast learning algorithm. It's pretty simple. Let's say, okay, we put all of the data together. We have a huge, a big affinity matrix, right? So in compared with the original kind of a clip or image classification, actually, we are trying to build a new kind of affinity matrix. It's not necessarily, okay, only the diagonal entries are positive, but it can be also some kind of off-diagonal entries would be positive, so that, okay, it can have kind of multi-to-multi mapping. So in this way, actually, it can accommodate this kind of image label data very well. And mathematically, actually, it's just a very, very simple kind of reformulate of the original clip contrast learning by having some kind of addition, averaging over different kind of image or different kind of label, given that, okay, so we have some kind of label data. So based on this, actually, we can find, okay, so the unified contrast learning can not only give you a very discriminatory representation, but also it's open vocabulary. So it can be generalized to so many domains. It can be used directly to do zero-shot classification or linear probing or any type of kind of task in the image level. So it definitely outperform their counterpart, which either only use the ImageNet 1K for the training or image text pairs for the contrast learning. Let me show you this figure. So this figure, okay, give you a sense about how it improved the performance. So on the left side, UniCell only land on image 1K. Actually, it cannot understand the kind of category out of the 1K. It's just project these two categories into the same location, right? This is very weird, right? But after you integrate the image text pair together, it can gradually learn to map, okay, the category, the semantic similar category or the visual similar category together in the feature space. On the other hand, if we think of, we're starting from the image text data. So we train some model from the YFCC, 40 million, and you will see, okay, this feature is not that discriminative. It can hardly distinguish the family species of dogs. It's just messed up together, right? But if we add some kind of image label data, because the image label data can help the model to learn very discriminative representations, so it will help you to distinguish different kind of categories very well. So this is why, okay, UniCell and how UniCell can help and achieve the best of both worlds for image classification, for image text matching, or etc. So talking about the image level, actually we introduced UniCell, but we do not want only apply it for the image level. We want to do it for the region level as well. So that's why we propose the grounded language image pre-training. The idea at high level is very similar. So basically, we want to, okay, associate or land the region in the image and the textual phrase in the either in the sentence or in some kind of synthesized kind of sentence, like consists of multiple concept, visual concept. So basically, the idea is that, okay, we still want to merge two types of data. The first type of data is phrase grounded data. It's very similar to the image text pairs, but with fine-grained kind of association between the region of the image and the text phrase in the text. And also we have the object detection data, like object 365, open image, visual genome. It's considered of 2.5 million image text box triplet. And overall, actually, we still use similar kind of learning objective, unified contrast learning, to learn a single kind of feature space, the single kind of model to achieve both the first grounding or open vocabulary detection, etc. And you can see, okay, after the training, actually, we already get a very good model, but this probably is not enough. So we have a seed model, we have a study model. We further use the study model to massively discover more kind of grounded image text files from open source data, for example, Leon, for example, the GCC, etc. And finally, okay, we have some kind of model level data or pseudo level data together. We put them into the original kind of human annotated data to further scaling up. And based on this, actually, it's achieved very, very good performance. Of course, we mainly work on the kind of COCO or some other kind of common domain image, but it did show that its performance is very, very good. It can, in zero-shot manner, it already achieve very good performance to some fully supervised, fully fine-tuned model on the as you can see from the top table. And we've also achieved the state-of-the-art zero-shot object detection and grounding on AVIS, which consists of over 1,000 object category. And it can be also applied in the wild. So you can use it to localize maybe some dog and also the smokes in the image. Actually, I think the training data barely contain this kind of data, kind of smoke or something like that. It can be also used to localize to detect all of the sea animals, etc. So it's pretty easy and generalizable. And even, okay, this type of image, we did not imagine it can be also used for this. So phrase grounding, okay, you have a sentence, you have an image, and the task is trying to associate the phrase in the first text and the region in the image. Okay, so this one we have finished, and basically the idea is that we want to train all of the closed set model, vision model, either image level model or region level model, actually to open vocabulary to multimodal vision, so that we can really squeeze the benefit from a huge amount of weekly level data, for example, image text pairs. And next, we were going to unify different type of tasks from different kind of specialist model. So I want to show this figure, the paradigm of vision data. So we want to know that, so if we have a large amount of data set, right? So, but this data set itself actually have kind of this kind of pyramid shape. From bottom to top, actually, we have some kind of rich data set and about costly level, like ImageNet, like Leon data. And also we have relatively better kind of semantic annotations and more kind of granularity, more fine-grained granularity. But later on, actually, we even have the pixel level kind of mask. But unfortunately, actually, usually the semantic annotation is very poor, but it's pretty fine-grained. So overall, actually, this is kind of the status or the distribution of the data set right now in the computer vision community. And we want to think a way to unify different type of data from different granularities, right? So we resort to an encode-decode architecture for its flexibility and the generality. So the observation is that, for the image level, for the region level, for the pixel level, so all of these kind of tasks, and we are seeing the convergence of the model design to use an encode-decode architecture. Like in image level, we have GIT, we have CoCA, we have Flamingo. In region level, actually, we have Ditra, we have Dano. For pixel level, we have Max Deformer and Max Dano, etc. So on the right side, you will see, it's basically take an image input, encode the image into some hidden feature, and have a text prompt or some hidden prompt, and to prompt the decoder to produce some output, textual or visual. And in this sense, actually, we propose X decoder, a generalized decoding for pixel, image, and language. So it's trying to unify image level and the pixel level. And of course, you can convert the pixel level to a box level, right? And based on this intuition, actually, we design very simple architecture. It's just a simple kind of decoder with the interleaved self-attention and the cross-attention. And it can take two types of input, the latent query and the text query, so that it can support different type of interaction or tasks. And also it have two types of output, the pixel level output and the semantic output. The pixel level output is trying to give you the very fine-grained mask. And the semantic output is trying to give you very kind of open vocabulary kind of recognition. And based on this, actually, we can use different routing for different tasks. We are still using the same suite of parameters, but we can have different routing for different tasks. For example, from left to right, we can do the generic segmentation, given some categories as a pool, and then the model can learn how to map the regions, how to decode the image into different type of masks and categories. And we can also do the reference segmentation. Let's say the query is the all on the left, then it specifically give you the mask, give the region of the all on the left. And it can also do the image text retrieval by align the image and some kind of text. And it can also do the image captioning and the visual censoring, because it can also generate the semantic output. So based on this, actually, we use two types of data. One is the segmentation data, and one is the image pairs. We just merge a lot of data and then train the model into end. And finally, we can get some very kind of capable model, unified model. And I will skip this. It's just showing that, it can be used to do a lot of open vocabulary segmentation across the board. It can be directly applied to all of the domains
Of course, it does not cover the material science, but it covers, for example, the self-driving or some other 3D layout, etc. So the overall message is that, okay, so we can train a single unified model to accomplish so many kind of open vocabulary tasks. And this is some visualizations. It did a very good job to apply to different tasks and different domains. And it can be also used to compose some kind of zero-shot new tasks. It can be used to do the region retrieval by composing the image retrieval the model can support, and also the reference segmentation the model can support. So basically, you have a query, you have a bunch of images, and you can specifically locate the region from a bunch of images, not just a single image. And it can also do the reference captioning. Basically, you can have a kind of a refer query, and then the model can not only give you a mask and also have a description about the region. And the last, I want to further introduce, okay, so how we can further make the whole system more promotable. So the intuition that vision task is not only about text, it's not only about, the single modality. So it can cover different modality and cover different kind of interaction mode. So previously, actually, almost all of the work, including XDecoder, only considered this kind of pipeline. So it have the text prompt, it have some kind of text and the visual output. But this is not enough. Visual by nature is not only semantic, but also spatial and visual. So that's why actually we want to expand, okay, this kind of encoder-decoder architecture to be more promotable, so that it can really cover as many possible scenario, as possible. So that's why actually we propose, okay, SIM, segment everything, everywhere at once. So you can see here from left to right, actually we can support so many type of prompt. It can be visual prompt. You can feed an image as input to ask the model to help you to localize the similar part of another image. You can use a text prompt, you can use a reference prompt, you can even composition, do some composition. So the whole pipeline is pretty simple. We are still taking an encoder-decoder architecture, but the difference between this work and the previous work is that we introduce 2 additional prompts. It's kind of visual prompt and also a mirror prompt to enhance the interaction capability with a human. And yeah, I will skip the details, but basically the model actually can be used to do a more kind of type of segmentation task, not only generic segmentation, open vector segmentation that XDecoder already covered, but also the integrated segmentation. And I will show some examples. So let's say, okay, give an image and you have some text prompt. Okay, I want to localize, okay, the small girl, and I want to localize the largest transformer. I want to localize, okay, the black dog. Actually, it will just suddenly give you the mask, give you the very detailed kind of location. And beyond, okay, we can also support the special prompt. So we have a point and we have a stroke, whatever kind of special prompt you can feed, and then the model can understand this kind of special prompt and can localize the region. And it can also do the compensation, as I just mentioned, the visual plus spatial. You can use another image and have a point on top of that image. And then, okay, the model can understand that prompt and then, okay, help you to localize, help you to segment out the corresponding regions from what other type of images. So this is pretty interesting and kind of, maybe probably very useful in the realistic scenarios. And it can be also used to do this kind of zero-shot kind of video object segmentation. If starting from the first frame in the first column, if you draw some stroke on top of the image, then the model can automatically propagate this kind of mask, this kind of region to the follow frames. So this way, actually, you can do the video object segmentation in zero-shot manner with this model which only trained on image data. And this still probably is still not enough. So previous work actually, even including SIM, actually only applied it to the object level. I'm sure, okay, people here are also considering, okay, different granularity of the segment, right? So it's not only about object, it's also about a part, right? So that's why actually we want to propose a new model. It's called semantic SAM. So we want to segment and recognize anything at any granularity. It's becoming more promotable than SIM and more controllable than SIM. And the idea behind this actually is pretty simple. I will skip this. The model architecture is still taking some kind of encoder-decoder architecture. It's pretty simple to use and pretty simple to develop. And the merit behind this semantic SAM is that, okay, it can really give you very rich kind of granularity output. From left to right, actually, it can be maybe a small part, it can be a single human, it can be multiple humans, something like that. So it's compared with SAM, actually, it can be used to output much more kind of granularity for this different type of images. It can even be more than the ground truth provided by SAM. And this is another example. So basically, it can have a very good performance as well. It can have more accurate kind of IOU used for prompting, or some kind of other prompting strategies. And if you apply this for different type of domains, it could be some handwriting images. It can even, extract the subwords from the handwriting. It can help you to extract a lot of information at different granularities. It can be even used to extract very, very complicated kind of, blackboard handwriting, something like that. So in the first part, I introduced you, so in the general domain, so how we are building the vision foundation, which can be much, much more promptable and unified and also multimodal and open vocabulary. But here, actually, I want to also introduce you to the most recent work, which is called Biometric. So it's kind of a very good application of our general domain kind of vision foundation to a specific domain, the medical domain. So as people just talking about. So the idea is pretty simple. So we are still want to, make the model more capable, more promptable. But unfortunately, actually, in previous work, actually, people, for example, applied SAM, and some other work actually it can only support the bound box prompt. So it's pretty narrowed, I would say. And here, actually, we have built a lot of works, and which could be much more promptable. That's why actually we directly and seamlessly apply this kind of model design to the medical domain. So talking about the medical domain, actually, we have different type of data from different domains, and also it can be different modalities. Non-modalities covered, for example, CT and MRI, X-ray, ultrasound, pathology, etc. You ever see, we are exhaustively creating a lot of data from different domains, and we are trying to use a single model, a unified model, to handle all of this type of data. And like I just mentioned, so SAM is not good. SAM is not sufficient. So if you look at this, if you only draw a bounding box as SAM showed, actually it can hardly handle the multi-object within the same bounding box. And also, if I want to handle multiple objects which with irregular shape, actually is not handled. It cannot be handled by original SAM or some traditional kind of segmentation. So we want to build a more promptable kind of vision foundation for medical domain. And again, so huge amount of effort. If you ask me to label all of the bounding box from the image, so why we cannot build a model that can automatically help you to enumerate, help you to localize all of the object of region of interest at once. So in this sense, actually, we built a Biometric. Actually, we are building one model for word prompt. So it's not only about text prompt, it's not only about spatial prompt, it's not only about these two, but probably was a visual prompt. So basically, we are building a new model, and we further integrate this kind of model with the with some kind of text encoder or text decoder, so that it can support open vocabulary settings as well. So based on this, actually, we want to segment well and recognize well. So it can reduce ambiguity with text, and also better segmentation results for irregular shaped object, and also scalable without a special prompt or a combination of this special prompt. From bottom side, actually, you can see, we can specifically localize one region. We can segment, localize all of the region and all of the categories. And there are some kind of visualizations, demos here. So basically, you have a text prompt, and then you just like chat with a human, right? So you chat with a human because the model actually can support different type of modality and also different type of prompt. That's why actually it can be very, very fluent and seamlessly, supported for the human AI interactions. And you can also, ask the model to help you to localize one of the cell types and also output the category of the types as well. And of course, new self-dot compared with one of the model. And the self-dot is just one thing, right? So we want to advocate that, this new model actually can be much, much more promptable compared with all existing model, including MedSAM or many other type of SAM. So yeah, the last slide I want to show this. So
I'm sure, okay, people haven't heard about, okay, the foundation, the language foundation, the vision foundation, etc., or even multimodal foundation. Our team actually built a lot of kind of multimodal foundation as well. But overall, I want to walk you through, okay, the advancement or the evolvement in the last maybe few years. So in both vision and language, actually, at the very beginning, actually, people are just developing some task with 3 models for classification, for detection, for segmentation in vision, or for translation, for summarization in language. But later on, actually, people are trying to do some kind of pre-trained model to learn some good representations, either for mask modeling, next token prediction, contrast learning. But this is still not sufficient, right? People really want to have a seamless interaction with AI model, so that it can accomplish some complex task. And later on, actually, we have even more unified model, which not only just provides representation, but also have a very good kind of prompting strategy, like in-context prompting, or chain of thought was maybe another type of visual prompting. But later on, people really want to build some general purpose system. It can have kind of human in the loop and have kind of our HF supporting, or etc. So I want to mention that, okay, so in vision community or in multimodal community, actually, there are less and less boundary between vision and the language in the first place. And later on, actually, people are trying to, okay, convert all of this kind of previous kind of, more kind of domain-specific model to more unified and a kind of general purpose model. But behind this, you will see, okay, people also needed to merge or unify different type of data, as I showed in the earlier slides. So the data itself is also kind of, distributed and also imbalanced. So how to cope with the data and how to design a very good kind of architecture to unify, to accommodate different type of data and the different type of input and output. This is still, a going project or ongoing effort in the whole community. But I want to bring you that, okay, so even in material science and especially from the last talk, I feel, okay, there are a lot of kind of exploration which we can do in the next. So yeah, basically this is what I want to share with you guys, and thanks for your attention, and yeah, enjoy your stay at Seattle. Yeah.
Any questions, like 2 or 3 questions before we turn over to panel discussion?
Yeah, please.
Yes, based on your experience, like adapting is kind of sort of focusing on like the open vocabulary aspect of adapting to like a specific domain, like medical. Did you find that there was any challenge with like very technical vocabulary that like needed some sort of way to bridge that, or needed to sort of default to more generic descriptive language? Or did you find that, today's language encoder models are sort of broad enough to capture that kind of technical vocabulary?
Yeah, basically we found it's enough. So because language model itself right now is very, very strong. So basically, okay, even for example, in Microsoft, we have some small language model like Phi, or we will have some even larger language model like Llama or some others. Actually, we found is the language model itself already learned so huge amount of knowledge from the work, from the Wikipedia, from maybe a lot of kind of literatures on medical or material science, etc. This knowledge actually is not fully used or leveraged by only, okay, from the language domain. But here, actually, we are bridge the vision and the language, and also squeeze the knowledge from this model by using some domain-specific data, for example, the medical data or some other type of domain data. Once you make it possible to squeeze this knowledge out, then actually the model itself actually can have some very good emerging capability to talk about, for example, the medical domain kind of terminology or the material science terminology. Actually is pretty good. So basically, we did not specifically design any kind of architecture for language model part to talk about the domain-specific kind of terminology or something like that. It's pretty straightforward to make it work. So this, yeah.
Yeah. Did adding other promptable domains, like when you went to the scene, did it take less data the more domains you added, or was it like more complex domains, like the video and stuff was making it harder? So when you went from like you had text prompts and point prompts, and then you added like region prompts and stuff like that. For every new type of prompt domain that you added, did it take less data?
I see. I think that's a very good question. So basically, so in SIM, actually, we have a very smart design, I would say. So basically, we have a which I call the visual feature prompting. So no matter what kind of prompt, actually we always, project or convert it into a visual feature prompting strategy. So given a bounding box, actually we extract the feature from the bounding box. Given the point, we extracted the feature around the point, and etc. So basically, the visual prompting strategy actually is pretty simple and unified. So that's why actually, as you just mentioned, I think this is a very good question. So basically, we found even with the same amount of data, we can directly convert the same amount of data into different type of prompt. And then we only use the same kind of visual prompting extractor to handle a wide range of prompt. There's no need to additionally add another prompt encoder to encode the bounding box, encode the point, encode the scramble, etc. There's no need for that. So we just have a simple one. And given the COCO data, actually we can synthesize some kind of different type of mode, prompt mode, with the same amount of data, and then we can scale up the different type of prompt types, and also get a very good performance across the board. So basically, this is very kind of interesting or very useful design for the model. That's why we don't need extra kind of data. We just use the same amount of data, but have more kind of capability. Yeah. Mm-hmm.
So I have a question about aligning text and images, especially in particular specialized text. So technical publications, and you have pictures there, and it looks like it should be very difficult. So the text is redundant. As a result, you have to filter out a lot of information to find what's in the text that's actually presented in the image. So are there any tools today available doing it for specialized in technical domains?
Yeah, that's a very good question. I think this was a very kind of open question in the general domain. So it's very hard. Like we showed, for example, in Glib, actually, we indeed train some seed model and use this seed model to build some more fine-grained association. And this way actually is not necessarily that scalable in general. So if the image text pairs or the image description actually are pretty noisy, as you just mentioned, or pretty long, actually, you cannot necessarily extract the useful correspondence or the association between the region and the text. So this is still open question, but people are trying to I think is trying to leverage the models or foundation model from different domain to make it more kind of scalable. Which means that, so for example, recently, a lot of work are trying to connect the vision foundation with the large language model foundation. So in this way, actually, we can leverage the large language model's knowledge or reasoning capability or some other kind of language prompting capability to help to annotate or help to build a more kind of grounded association compared with the previous model, like what we did in many works like Glib or Sim, etc. So this way is better, but probably it's still not that kind of perfect. But it's still open question. So people are trying to see whether, for example, use a multimodal larger model as an annotator, whether it's better. It's still open question, but this is a very good question, I would say.
Thank you. So let's turn over to panel discussion, and we asking invited speakers to see it here, so we'll bring more chairs.
See, do I have my watch? Oh, here's my
I'll keep you here because to help when you send that, just in case.
Let me.
Yeah, nice to meet you. Yeah, great talk. Very interesting.
And we have one of our panel members on the screen.
Liz, can we just test your audio one more time?
Sure enough, here I am. Can you hear me?
Yes, great, thank you.
Good, thanks.
So we'll start with a seed question, and then you're welcome to start answering your questions at any moment. So don't be shy. I have a question. So the one I would like to start with is about computational scalability of all these methods. So when we talk about foundation models, vision transformer, let's say it's n squared, where n number of pixel pitches, so tokens. And in some applied domains like biomedical imagery or satellite imagery, when we have where we have to deal with very large images in terms of pixel dimensions, like in biomedical, you have to deal with like 200K by 200K pixels computationally, like using conventional vision transformers is not doable. So my question is, do you see that there is increasing trend in material science imagery to deal with such huge images as well? And so in other domains, problem domains, people have been working on hierarchical approaches to address this challenge, but so far I think it's still an open question how well those hierarchical transformers would work. So what's your take on large scale, so large images and materials domain, whether it's increasing trend to deal with them or you're already doing with them? So maybe, I don't know, maybe we'll start with Liz.
Sure. So there's no question that we have some high resolution image methods that are widely used, things like mosaic images for macro scale photography of samples. Certainly the trend has been for higher and higher resolution on the digital cameras used in our microscopes these days. Typically, we end up, when we use those images in computer vision approaches, we end up just subsampling. And that's typically because the things we're interested in are at smaller length scales anyways, and we can do so. There are exceptions, and one exception that I think is very significant is in the realm of synchrotron data. So synchrotron data is using synchrotron-based sensing methods is one of the ways that we are able to acquire three-dimensional microstructural information about materials. And the trouble with synchrotron data is, first of all, it's huge. It's terabytes of data for every experiment. And second of all, it doesn't, the raw data at least does not lend itself to subsampling. And so we have these very large images, and we have a very large amount of these images in the raw data sets. And that is an area that's very ripe for computer vision approaches.
Oh, yeah. So maybe I can share some kind of recent work we did with Microsoft Future. So there is another work called Giga Plus. So that work actually, we are exactly handling, okay, the very large, big resolution. I think maybe it's each of the pathology image actually contain maybe thousands of slides, and each of slides maybe okay thousands by thousands kind of resolution. So in that work, actually, we definitely cannot extract the patch embedding and put one of the patch embedding into a single reality model. But we indeed borrow some idea recently proposed by the community, which is called a long net or other type of local attention architecture. So basically, actually, you will say, okay, this local attention is very similar to the convolution network. So we want to constrain the region, the attention scope much smaller, so that we can significantly reduce the computer cost, and so that the whole model actually can handle maybe a huge giga level kind of pixel. So this is one way, and another thing I think people probably need more study that in this is actually even myself actually think about is it
which transformer actually is really often necessary thing, or connex actually is pretty good enough. So like people here actually probably use a lot of connex. Actually, probably you also found okay, it's not necessary that connex is worse than the visual transformer. So basically, you will see if you really want to cope with very high resolution, then you need to find some way to turn the global attention or global interaction into some kind of local attention or sparse attention, etc. This is one good way to think about it. Yeah.
Yeah, so I think that there is definitely, well, I think there is the opportunity to start using more high resolution and larger images in microscopy. I mean, the microscopes are getting better and better, higher resolution. We're taking them at higher frame rates. I was working with a microscope that was taking 4K by 4K images at 4,000 frames a second, and it was just filling up hard drives in a session. And that's so and there's like CT scans and stuff. So we're definitely generating tons and tons of data. But it is, and so I think it would be awesome to leverage all of that data. Currently, a lot of work that I've been doing, often it's not as necessary. I'll either do patches or downscale the images. But we could leverage the high resolution because like the materials properties can rely on multiple different scales simultaneously. So it'd be great to attend to multiple scales simultaneously or different parts of the region simultaneously. And convolutional neural networks work really well. Like they have a really useful implicit bias that nearby pixels are related to each other. But if you have two parts of the image that maybe it could leverage information from both of them or at different scales, it takes several convolutional steps before that information is exchanged, and it can make it information from that. Now, full attention doesn't really scale well to like every pixel attending to every other pixel. But there have been work on like axial attention where every pixel in like a row will attend to every other pixel. Then in the next step, it'll be the column. And then they'll do like an interface so that they can like any pixel can attend to any other pixel in 2 steps. But that is a lot more data required for training than CNNs. And so I personally I'm not aware of work at least in material science where people have been able to leverage the high resolution stuff with that type of method yet. But I think with enough training data, we could, and cool foundation models, we could start leveraging stuff like that. And maybe more tuned types of attention, not just axial attention, but like region attention, different shapes of the region attention, like sparse attention, could be very interesting to explore. And I think still a lot of experiments we have to do to figure out what's going to work best for our domain or in general.
I'll just throw in a final piece on the experimental side and collecting the big data components is we often look at the cost benefit analysis. So while we can go to synchrotrons and get 3D data and it looks really cool from the experimental perspective, do we need that to answer the question at hand? Or are we okay just going to the SEM that's down the hall and getting the images from that? And so it comes to the perspective of, I think once we start getting enough of these really big data components, we're going to learn more needles in the haystack that we didn't know we could learn from them. And so we will see the benefit. But for the costliness at this point in time, it becomes hard to justify some of the experiments when, you know, you might have 10 days in a year that you can get your samples in a synchrotron, but you can get your samples in an SEM every hour if you want to. And so what's that cost trade-off?
So I would like to ask one more question about just your thoughts about tokenization strategies. So when we talk about foundation models, usually it's just uniform grid of pixel patches. And this doesn't look optimal. So it's just happened because of convenience. Any thoughts, or are you aware of ongoing work about irregular grid tokenization approaches and whether they make sense in material imagery, or maybe it's good to use just uniform grid superimposed on top of materials. Liz?
Well, I'll admit, Alexei, I haven't thought about that in this context. But our colleagues in materials modeling and simulation have thought about that for years and years in the context of physical models, right? Finite element models, phase field models, point cloud-based models, and so on. There seems to me to be a lot of prior art in understanding how to use irregular grids to optimally capture the regions of importance in a material, but in a different domain from computer vision. So perhaps there is some synergy there that would be usable. The other thing I would say is, of course, graph-based models are excellent for this, and graph-based machine learning models are being used in this domain. And in a sense, every graph is an irregular grid representation. So that's another direction to think about. But those are my two ideas off the top of my head. Perhaps some of my fellow panelists have more concrete ideas.
Yeah, maybe I can share two things. So really, actually, indeed, in the general domain, kind of vision community, including myself, actually have to think of how to get rid of, as you just mentioned, this kind of grid kind of tokenization. So basically, I would say it's not trivial. So even though we are seeing some works trying to, like just mentioned, clustering the pixel into super pixel, or clustering the tokens or the features into some irregular shape. People are doing this, but the problem is that this kind of clustering or this kind of tokenization with irregular shape actually first it will face some kind of difficulty of scaling up. So basically, you need to have some kind of supervision to tell your model how to divide, how to kind of decompose the whole image into some irregular one. So really, actually, we have very less amount of kind of supervision, even though actually, for example, in general domain, we have S1B, actually it consists of 11 million fine-grained masks, but this is still not far from sufficient and much less than the general kind of foundation trend, the data used by general foundation training, for example, Lion consists of maybe hundreds of million or even several billion. So the supervision is not enough. And I think this is one thing why, people are trying to push this direction, but the benefit or the return of interest actually is relatively low. Only if, you really have a huge amount of data, which can provide you a huge amount of kind of irregular kind of sub-regions from, so that, the model can really cover different domains, cover different kind of granularities, etc. Then I would say, this could happen. But right now, actually, people are trying to do that, including myself. And we are seeing some big signal, which can probably outperform the regular kind of tokenizer in the context of a multimodal language model. So, I'm working on some kind of multimodal language model right now. So basically, we can see some, but it's not that strong compared with, you only leverage a grid-based tokenizer like a Clip, like Convex, like a VQV encoder, etc. So yeah, people are doing this. Yeah, basically.
Yeah, I don't have a whole lot to add. I think that there is a lot of value there. I think I'm vaguely aware of some research, especially in self-driving cars, where there's an issue of you're looking at the whole field of view and you need it fairly high resolution to read a street shine way over there, but you can't process the whole image on that level of granularity. So they'll look at a lower res, like kind of a hierarchical, maybe attention thing, and then say, oh, I know there's something important over there, like a sign or a person, and then focus on that. I think that could work well in microscopy because there could be like a defect, for example. You're looking at a huge field of a high resolution image or skin or something, and it can't process it all in super high resolution, but it can maybe process enough to say, oh, there's something interesting here. Even if it's irregularly shaped, then I can pay more attention to that. Or maybe like add a mask to it, like what you were doing with the video. Maybe you could do something like an irregular mask shape that then goes for another iteration of, but that's just the top of my head, though, not aware of what's going on.
It's beyond the
So any questions, please ask.
I have one that's, we talked a lot earlier about, how much training data do you need for a downstream task, whether it's sort of, a lot, or it's few shot, or it's one shot, or it's zero shot in some cases. Sort of on the flip side of that, how much test data do we need to use some of these like very few shot or zero shot models for an application? And sort of comfortably use them in.
Can talk about forensics.
If I may, that's a great question, because I think that's something we underemphasize. When we are in the data limited regime, our inclination is to save as much data for training as possible and to test on very few examples, typically, because we want as much of our data used for what we consider the productive part, right? The training part. And I don't think enough studies have been done on testing the uncertainty quantification of our results based on enlarging the test set. I think that's not just a problem in our material science computer vision applications. I think that permeates the field. There's a strong inclination to present a single number as the accuracy or the IOU or whatever score you use, the F1 score, without error bars. And the reason there aren't error bars on that number is because we don't have an appropriately broad test set. So I think that's a really good comment.
From the forensics perspective, we have to know the limits of our data, because like Liz was just saying, you'll be able to make a prediction on something, but it could be an incredibly wrong prediction that you have a high confidence in. And that is a horrible situation. And so if you're going to make some type of prediction, you have to know, is this within the bounds of what your model is capable of doing? Because if it's not, and you make a prediction on it, there's real consequences for it. So that is really, really hard to do. So right now, if we talk about using it in nuclear forensics, we talk about using it in an extremely narrow scope where we know that it works in. And if it deviates even a tiny bit from that, we don't even consider it because we don't know the limits of what it can and can't do. And so that's really what our goal is how do we expand that scope.
And if I may add, I had a student do an unsupervised classification exercise with k-means on a set of data, a rather large set of data that we had. But I asked him to do an ensemble of training and test splits. And the test accuracy varied from quite poor to excellent across the data set, depending on what test set you got, right? You know what your training test split was. So that tells us that we don't always know from the limited test data that we set aside how good our model really is. We could have been lucky and gotten a great test set, or we could have been really unlucky. Perhaps our model's actually quite a bit better, but we're unlucky in our test set.
I have a somewhat vague and slightly open-ended question about how we can use the various tools that we have developed to feed back into the data acquisition side of things and use these various things to drive the instruments that we're doing so that they take more interesting data and that they potentially we can, as I think we alluded to, ignore the less interesting things so we can streamline our process and just focus on getting the data that we need to solve the question at hand.
Yeah, so that's a very good question. And I think one way is to use active learning or Bayesian optimization approaches, or you can do like optimal experimental design. But yeah, instead of using like a traditional design of experiments, you can do set up an experiment that leverages the information you already know and the relationship from processing of properties, for example, and then you can target experiments that will give you optimal information or like expected value from that experiment, and whether that value is defined as maximum uncertainty or like maximum expectation of improvement. Yeah, so that's one way that you can guide acquisition in a non-heuristic way.
Yeah, I think we can also borrow some kind of idea or inspiration from, for example, the language model community, even the ChatGPT, right? So basically, they have some kind of after this kind of supervised fine-tuning or something like that, and then they usually have some kind of reinforcement learning from human feedback or reinforcement learning from the AI feedback, something like that. So talking about from human feedback, actually, basically, they have some kind of sparse kind of guidance from the human, and then okay, this kind of sparse guidance actually can be integrated, can be merged to the to the system, and finally it can gradually improve the performance. I think this way could be potentially applied to some other domains, for example, vision domains or multimodal domains, but it's still a little bit harder than in language domain, because in language domain, actually, the communication or the interaction mode is just language. But in the multimodal or vision domain, actually, the community model is not only language, which means that, okay, you cannot use your language to express what of intent very precisely for your model. So it's pretty different in this sense, right? So you need to think of other kind of maybe problem strategy or some kind of interaction mode, so that you can really convey the precise knowledge from human user, from another AI model to your model, something like that. So this is what we need to think about more carefully in the context of vision or multimodality domains.
Yeah, I slightly more general version of the previous question. I know, like in software development today, these AI assistants have been trained on all software on the web, and really as a software developer today, you have to be using these tools to be efficient. I'm curious to get your take on how quickly we'll see those kind of AI assistants be useful for chemists, material scientists that are working out there. You can imagine, being trained on the corpus of scientific literature out there on the images that you use day to day. Are we close to having these AI assistants be useful for the domains that you work, the scientists that you work with? Or actually, do you even use any of these ChatGPT things yourselves to accelerate your work?
Yeah, so I think like they're getting useful. So I think the material science domain, nobody's going to dump a lot of money making a bespoke solution before they start entering the medical domain and making medicine, making chemicals. But we can use, like, I mean, I use GPT all the time to help code, to help write emails, and it's definitely getting more and more useful. And I think like it's the worst it's ever going to be from now on. So the next one's going to be even more amazing and helping us even more. And I think that probably it'll start being really useful for doctors, maybe seeing patients, scanning all the corpus, like maybe they like have their doctor's notes or even a recording of the doctor's visit, and then the AI assistant's like, hey, I found these papers that seem really relevant to your patient, or like, here's a new drug that was recently FDA approved. But so I think that'll happen first, and then it probably, my guess is then it'll start being useful to the material scientists. But I think it's already being useful and will only continue to get more useful, helping guide experiments. I think the hard part is getting the information into the model, like how does it know what I'm thinking? How does it know what experiments I'm doing? I need a way to like get that into the model so that it could then help me. And like, I guess the text prompts are pretty useful, but I think we'll continue to see more great ways. So I think it is going to make a huge impact in our domain and every domain.
I want to share a little bit funding in the general domain. So when we're talking about the, for example, ChatGPT, actually we are actively work on some visual function for GPT-4b or GPT-4o. We recently proposed a visual function called Mark. So this
visual problem strategy is pixel level. So which means actually you just draw a bottom box or put a mark on top of the image. That's it. So and ask the GPT-4V to answer the question corresponding to the mark you draw on top of the image. And it suddenly unleash the power of the grounding capability for GPT-4V. If you directly use GPT-4, you actually cannot understand, for example, a single or a very small region very well, or look at the single small region very well. So, but with this kind of visual prompting, which is some analogy to the language problem like chain of thought or some other type of prompting strategy, it's just focus the model on a small region that provided or asked required by the human user. And suddenly, actually, the visual prompting is pretty good. And we already seeing a lot of people applying this kind of simple, very, very simple kind of visual prompt strategy for anomaly detection for different domains. For example, even I probably noticed a paper, even anomaly detection for material science, some kind of micro, some image, something like that, and also medical domain or any other type of domain. It's pretty straightforward. And the reason why it works is because, okay, the GPT-4V or GPT-4, actually the foundation model itself actually already covers huge amount of data. Maybe even from the material science or medical, many other domains. So that's why actually it works out of the box. Yeah, I think it's very interesting for us.
I might get one more thing. What I'd like to see is like embodied agents, which I think will, like robots that I think should be coming online like pretty soon, the next AI revolution, hopefully by 2030. But we just paid like $700,000 for a very limited robotic lab. It has like a 6-axis little crane controller. We can synthesize chemicals. It's hooked up to machine learning algorithms to like design the next experiment. Just it runs into a loop with active learning. But I mean, they say that like the Atlas robot's like $150,000. Maybe you hook up like the next AI to it, maybe you double the price. Even if it was like 500 or 1,000 or $1 million, what it gives us is the ability to automate all our existing labs. I think it would be great because we're going to need to do like a certain number of experiments to find the next best material. And all our labs are just sitting there not being run at night. They can be generating data. We could think of research like we think of factories where an idle factory is money lost and we're losing research. And I think that we could really accelerate things with embodied agents. So that'd be a cool way to apply our domain.
I'd love to see it applied across modeling scales. So going all the way down to like a molecular dynamics model, up to a phase field model, up to this is the exact particle microstructure that we see. And I haven't seen too much that's been able to couple that together. But I think when we start thinking about predicting new materials in the future, that's where we really got to get it. It's all the way down to understanding why are we seeing these exact microstructures on the molecular dynamics scale. And if we can do that, which we can, we just can't take them up to a micron scale, like that computational tool for modeling a micron scale particles. I think that would be lovely to see this.
So this is just like a sort of open question or curiosity. So, for example, if you are looking at SEMs, right? So one SEM may be like a totally different material and another, so you might have the same intensities or the same almost structure that you see, but it means totally different things. And so this is why we have all these fragmentations, right? We need all these bespoke models, like you said. So is there any standard we can set that can allow us to sort of differentiate between these materials, or that, so we measure it in such a way that we can also differentiate the materials to some extent? So then we could have just a single model that can try to segment everything.
I would jump in just to say that we always have the saying it's a feature, not a bug. Much of the science behind microstructural understanding is related to the commonalities between microstructures of different material systems. And so in some sense, when we see microstructures from very different materials that are very similar, that's actually because we believe there are some underlying physics that are common between those material systems, more important than the chemical composition. And that's something that that these wonderful pattern matchers, these AI-based pattern matchers, are good at bringing out to us. That said, we know that in these deep learning domains, the systems can see differences that are more subtle even than human experts can detect. This is well shown in the medical realm. And I would expect that the same thing would be true in materials as well. For example, if I were to have a simple single-phase equiaxed polycrystalline microstructure, all the topological and geometric features are the same, whether I'm looking at a metal or a ceramic or even certain crystalline polymers. But there are subtle features that are probably different. Aspect ratios of grains, even color correlations in an SEM where there's contrast. And so I think that that finding commonalities is a benefit of this method, but also sensing subtle differences as well. I hope that answers the question.
Yeah, I think I hope that, yeah, I mean, foundation models like maybe will be more applicable to, yeah, different materials that are behaving, they might not be identical, but they're like behaving similarly. But, you know, I found that a lot of times you have to meet in the middle between like the data acquisition and the robustness of the AI to changes. And like, yeah, I guess like, yeah, it's not always good to have one model that can handle all the different types of things. Like one time I was like making a model from 2 different sets of images from 2 different sources, and I tried to make one unified model, and it was better to have 2 separate models. But I could totally see a more general like foundation model maybe could, or like different like domain adaptation techniques, for example. Like there are techniques to make them work well together, and so yeah, I guess that like it just depends, and also like how much time you want to throw at the problem.
I agree with this actually. So even though we have been building foundation as planned, but in general, actually, I think it's not always the correct or to always think of building a unified model to unify all of type of tasks. And as Joshua just mentioned, actually, it's not. It's probably that okay, these 2 type of tasks actually are indeed from different domains, and they are actually have a huge gap in between. This way, actually, unification is probably will cause more kind of hurt. But at a high level, if the foundation model, if the task coverage is a very big scale, then I think the upside is for the building foundation is that okay, so many of the tasks actually are just interpolation, interpolation of the task you are calculating. So this is a good benefit from the building foundation. So you pull down all of the data into the model, and then okay, so some kind of imaging capability come out from the foundation model. And then if you better fine tune, have some kind of parameter efficient fine tuning with this kind of foundation model, then you suddenly have a very, very strong kind of domain specific model just coming out. So this is kind of benefit of building foundation. You just want to the model to expand the scope of the task scope, and then your task of interest could be one point inside this scope, not outside the scope. This is good part of the foundation, I guess.
Any other questions? The final question. Anyone?
I have a question. I'm not very familiar with both computer science. I'm actually from mental image analysis and pathology. So actually, I wonder in this kind of downstream task prediction, is it more about measurements, or is it more about global property that is actually depending on some unknown specific location where the domain has like high interactivity? I don't know if my question is clear enough. So there's two ways, right? One way is you want to measure how many of those components and what's the overall size and the area. That's one way. Then it's like segmentation and measure. That's one way. Or of course, there's also a way to just do a whole slide, whole image level prediction of this measurement. But on the other hand, in terms of whole image prediction, when the whole prediction is it depending on the whole area, or is it on the specific location that is most critical for relevance? That makes sense. Yes.
Yeah, that makes a lot of sense. Yeah, no, it definitely.
Sorry, just to start the interruption. My point is, if the second case is the case, right? So in some sense, you can circumvent the whole slide level, attention module, right? In some sense, you're really trying to find the weakest point of the whole image, right? And then if it's the other scenario of measurement, then it's localized segmentation. You don't really need the whole side.
Yeah, I would say it's definitely very material dependent. Like crack propagations can be very dependent on like the area in front of the crack tip, I think. And other things may require finding the weakest link in the whole material, the weakest like path of deformation. Yeah, I guess it depends on the application, I would say. So I think both tools would be useful. Yeah. Did I capture your question right? And yeah, so it's a very general way to answer.
Yeah. I mean, yeah, because my question is very general. So, yeah.
I think it's in some sense related to computational complexity. Instead of using full attention, you can focus on some regions, and in remote sensing world, what's fun also, like small scale feature extractors still useful, though you have to process very large images. They don't solve all the problems, like all the object detection and recognition and huge image, but as an intermediate step, you can still use pre-trained feature extractors. Pre-trained on smaller images than real satellite images. So, in conclusion, I would like to thank our invited speakers, in person and the remote one. And the workshop was the team effort, and I would also like to thank people on the organizing team, and in particular Catherine, who's dealt with Zoom issues, and people on the program committee who were doing submission reviews. And on that note, the workshop is done.
Yeah.
Thank you so much, everyone.
Thank you.
Thanks everyone who joined us on Zoom.